Now, maybe you're in this course because you want to ace coding interviews. And that would be totally fine, though this course is for everyone who's interested in algorithms, whatever your reasons might be. But if we're briefly sticking to that interview situation, you might get an interview question like this one. You got a list of items where every item has a value and a weight. And then you got a bag which has a maximum capacity, a maximum weight it can hold of X. And that could be any number in kilograms, anything like that. So now your goal is to write a program that basically calculates the items that should go into the bag to maximize the value of the items, whilst of course ensuring that you don't exceed that maximum bag weight, so that capacity of the weight. And here's an example with some numbers you might be getting or you might then derive on your own. A list of items, let's say, A, B, C, and of course that could be concrete items like bread and butter and whatever, but here it's A, B, C, and every item has a value and a weight. And then we have this max weight, let's say it's 8, and our goal is to derive a bag and derive what should be in the bag. And in this very simple example here, that would be the items A and C, because combined they have a value of 13 and a weight of 6. So the weight is below that weight of 8 and the value is a pretty big one. Now, we could have also just put item B into the bag, since that also has a weight of 8, so it would fit in. But with that, we would only get a value of 6, so that wouldn't be the maximum. Now, to us humans, that's a pretty straightforward problem, and we can solve this pretty quickly. But if you would need to write a program, if you would need to write code that solves that, you would probably quickly reach a point where this becomes difficult. Now, this task here is a very popular problem, which is called the knapsack problem, and it's often asked in interviews. Throughout the course, we will solve it. We're not at this point yet, but we will solve it throughout the course. But I already wanted to put it out there. That's the knapsack problem, and we'll revisit it later. Now the question is, why are companies asking for something like this? It's probably not a problem you will need to solve when you work at Google or Facebook, right? Their users don't pack bags. Well, actually, you might need to solve similar problems. If you're responsible at Facebook for coding or for working on the part where users can create groups with a maximum number of participants and so on, you might actually have similar problems. But most importantly, questions like this are asked to check your problem-solving skills. Because as a developer, you need to be able to solve problems. You're getting hired to solve problems. And even if you're working on your own as a freelancer, you are solving problems. Or if you're working on your own private projects or on your own startup, you're also solving problems. As a developer, you're always solving problems. And with that, let's take a step back and have a look at the term algorithm. What does this actually mean, and why do we need algorithms? Now, what is an algorithm? An algorithm, in simple words, is just a sequence of steps, of instructions you could say, to solve a clearly defined problem. Back at this knapsack problem, we would have to come up with code, with an algorithm therefore, which gets a clearly defined input, which has the goal of solving a clearly defined problem, maximizing the value and keeping that weight in mind. And then you have to come up with steps that solve that problem. And that's what an algorithm is about. We have these two key parts, a sequence of steps and a clearly defined problem. And these are the two things that in the end make up an algorithm. And the same steps with the same input should always lead to the same solution to a problem. That's the idea behind an algorithm. And therefore, of course, every program you're writing is an algorithm. The entire code, all code combined in a program, is an algorithm. And of course, such programs can be split up in many smaller algorithms. If you add a click listener to a button and on every click you add a number to another number, you also have an algorithm there. It's all an algorithm if you want to think of it like that. And as a programmer, as I mentioned, your goal is to solve problems. You need to be able to do that, and of course, you need to be able to do that efficiently, which means for a given problem, you want to find the best possible solution. And now, of course, there are different ways of defining the best possible solution. And now, of course, the question is, what is the best possible solution to a given problem? Is it the algorithm that has the minimum amount of code, so the least amount of code? Is it the algorithm that takes the least amount of time to finish, so that has the best performance? Is it the algorithm that uses the least amount of memory, so that it doesn't take up a lot of resources on the computer? Or is it simply your personal preference because you like code snippet A better than code snippet B? Well, of course, we could discuss about that. The best possible solution very much depends on the circumstances in which you're working. But often it will be the best performance you're looking for. That is typically what you would consider the best possible solution. The algorithm with the best performance, so that it takes the least amount of time. And with that, the question of course is, how do we measure performance? Because if we can't measure it, we can't judge it. Now, in order to find out what the best possible algorithm is for a given problem, we need to be able to measure performance. Now let's see how we could measure it. And for that, let's take an example problem. Your goal is to write a function that takes one number as an input and then builds the sum of all the numbers leading up to that number. This function could look like that. It's a fairly trivial function. We get a number as an input, n, and then we have a result 0 initially. We have a for loop where we simply go through all the numbers up to n, including n. We add that to the result and we return the result in the end. We can simply write this together here. I'm simply doing this in the Chrome developer tools in the JavaScript console there, because for the moment, that's all we need. It's just a very basic first example. For the rest of the course, we will use code files, no worries. But here we could add a function, SumUp, which takes n as an input, curly braces, opening and closing, and between those hit Shift-Enter to not submit it, but to add more code in new lines. And then here we have the result, which initially is 0, Shift-Enter, add a for loop, where we have I, which is equal to 1 initially, because we started 1. We could include 0, but it makes no difference. We want to go up all the way, as long as I is smaller or equal to n. And then we increment I. Curly braces and Shift-Enter. And then in the loop body, we add I to result. And then we, in the end here, return result. This is the function that will solve this problem. If we hit enter, we now submit this function, and now it's stored here and we can use it. So for example, now we can call SumUp for 3, and I get 6 as a result, which makes sense because 3 is essentially 3 plus 2 plus 1. These are the numbers leading up to 3, and summed up they give us 6. And therefore SumUp for 4 gives us 10, because that's 4 plus 3 plus 2 plus 1. So this is the problem solved. This is our first algorithm. But how can we now measure the time it takes? Well, for that, I'll clear that. It's still stored in memory. I just cleared the console so that we have more space. For that, we can measure the time when we start and the time when we end, and simply take the difference. For that, I'll add a start variable, which is 0, and an end variable, which is 0 initially. And then here we can write start, and in JavaScript, in the browser, there is a performance object on which we can call the now method, and this gives us the current timestamp. Now I can set start equal to that, then call SumUp for, let's say, a value of 5, and then end is performance.now. And with that, we can just output end minus start. Here in the console, you can just type it like this and it will print the result. And this will give us the amount of time this took to execute. So if I hit enter here, this is the result I get. Okay, let's now repeat this. For this, you can press the up arrow key. And let's say we use 10 now instead of 5. If I hit enter, you see I get pretty much the same time. Actually, exactly the same time. So it looks like it takes exactly the same time, no matter what we enter here. Well, let's confirm this by using, let's say, 1000 as a value here. If I now hit enter, oh, okay, I get a different time. Roughly 3 times as long as it took before, right? It was 005 before, now it's 015. So it's definitely not always the same time, but it seems like there is no difference between 5 and 10. Well, that's the problem with measuring time like this in hard numbers. If we do this, we have a lot of influencing factors that have nothing to do with our algorithm. For example, and easy to imagine, the computer you're running this on matters. I'm running this on a relatively new MacBook, and of course that's a fast device. On older devices, you will see different numbers. But even on this MacBook, I don't always get the same result, because it depends on how many processes are running in the background, on the browser I use, on the open tabs in the browser, and on a lot of other things. In addition, the browser does certain optimizations behind the scenes where it caches my function and caches values, so that even for one and the same value, I will not consistently always get the same output. So measuring time like this is not a great idea, and especially for very small values like 5 and 10, it's very unreliable. Now, still, let's see it for some bigger numbers. So instead of 1000, let's run it for 10,000. And now let's run it for 100,000. And let's run it for 1,000,000. And be careful, don't enter a too large number here, because eventually it will freeze your computer. But 1,000,000 should work. And you see we're getting results here. Now let's run it for 10,000,000. That should still work. And that will be the last number, 100,000,000. Now, we see a trend at least. It tends to take longer for bigger numbers. We have this strange result for 100,000, which took longer than 1,000,000. But let's ignore that. Generally, what we can roughly say is that the bigger the number, the longer it takes. And also, roughly, especially for the bigger numbers, we can say that for 10,000,000, which we have here, it takes around 5 times as long as for 1,000,000. For 100,000,000, it takes 10 times as long as for 10,000,000. Now, if I try this for 1,000,000,000 by adding one more 0, it gets stuck for quite some time, but then again, it's roughly 10 times the time it took for 100,000,000. So it looks like for big numbers, we roughly have factor 10 when it comes to the performance, when we have factor 10 here on the number. I use 1,000,000,000 instead of 100,000,000, so that's 10 times 100,000,000. I get 10 times the performance. So this looks like the relation. It looks like if we double the number for big numbers, or we take it times 10, the performance is also doubled or taken times 10. And indeed, this is how we should look at it. We shouldn't care too much about the concrete numbers, because those depend a lot on the environment, especially if we're working on small input numbers. But we should care about the general trend, especially for very large numbers. So for this function, if we would want to draw a graph for this function, it would roughly look like this. Now we saw for small numbers it was very unreliable, but for bigger numbers we saw a linear trend. And theoretically that should be there for smaller numbers as well. There we just had too many influence factors. But generally we can say that for this algorithm, A bigger number, a bigger input number, leads to more loop iterations, and hence the time it takes to execute this function increases. And for this specific function, and therefore for this specific algorithm, we saw that it seems to increase in a linear way. Especially for the bigger numbers, we could see that if we take the number times 10, the time the function takes also is essentially 10 times the time it took before. So we have a linear growth function there in the end. The factor by which we increase the input, so in this case n, is the factor by which the time the function takes increases. It increases in a linear way. And that's how we judge performance when we talk about algorithms. We don't care about the concrete numbers, but we care about the trend, you could say, about the function of time, so that we can basically make a statement about the performance of an algorithm based on the time it takes in relation to the inputs. Not speaking about absolute numbers, but about this function, about this trend, this line in this chart here. And we also call this time complexity. So in this case, we would say this sum up function and the algorithm in there has a linear time complexity. Now, of course, not all algorithms in JavaScript take linear time. We saw this here, this linear time function, but we also sometimes have algorithms that take constant time. So where the number of inputs has no influence on the time this algorithm takes. And actually, I can show you an example for constant time based on that example we just saw. Here I'm in a new tab, and now I'm going to rewrite this SumUp function in a different way, because that's typical in programming. Often you have more than one way of solving a problem. I mean, if we wouldn't have alternative ways of solving a problem, we wouldn't need to measure the performance, right? This entire idea of finding the best algorithm and of finding a way of comparing performance of algorithms, well, that entire idea would be useless and worthless if we only had one solution per problem. But of course, in programming, you can be very creative and you can find dozens or hundreds of solutions for one and the same problem if you want to. And that's why we need a way of comparing performance, which is exactly what we're working on right now. And here, previously, we solved this SumUp problem with a loop. Well, it turns out we can solve it in one line with a mathematical equation. There is a pretty nice mathematical formula that does this for us, and it looks like this. You divide n by 2 and then multiply the result of this with 1 plus n. Now this might look strange, but this is just math. And this is just a math formula, which you can derive in mathematics, that gives you in the end the sum of all the numbers up to a number. I can prove that if I save that function, if we call SumUp for 3, I get 6. For 4, I get 10. For 5, I get 15, and 5 indeed is 5 plus 4 plus 3 plus 2 plus 1. So this works, and this is just math. Now here's one important difference to the solution from before. Here we have no loop. We have one mathematical equation. Now if we try to measure this, so if I now copy this measurement code here from before, for a very large number, you immediately see this is much faster. And actually, it doesn't change much no matter which number we use. We just have this deviation based on the system we're running on. Now it even took 0 milliseconds, that's fast. But generally, you can see no matter which number I enter here, it's super, super fast and it doesn't really change. We definitely don't have a trend as we had it before, where large numbers led to a much longer execution time for the function. Now, the execution time of this function is pretty much always the same, because in there we have no iteration, we have no loop, we have just one mathematical term which is executed no matter which value we feed in for n. And that is such an example for constant time. The time it takes to execute the function is always the same, no matter which value n has. And this is not only an example for constant time. This also shows us why it's important to know about time complexity and why it's important that you as a developer are able to figure out which time complexity a function has. Because for this given problem of solving up all numbers up to n, if you would have decided that this loop solution is the best possible solution, you would have taken the slower algorithm. We were able to find a faster one after all. That's why measuring performance is so important and why you need to be able to write algorithms, but why you then also need to be able to compare different alternatives to then find the best one. Now, besides linear and constant time, we also find algorithms that have quadratic time or even cubic time, and a lot of other time complexities as well. Pretty much anything is possible here. You can have all kinds of different graphs here that grow faster or slower, but these are some of the common ones. Now we have one problem though. I mentioned that we don't care too much about the concrete numbers we got, for a good reason, because they are influenced by a lot of factors. Now still, we were able to identify some trend here. We were able to identify that for the iteration solution with the loop, for big numbers, we have a linear relation between input and time it takes to execute the function. And for our one-liner here, we saw that the time doesn't really change a lot. It certainly doesn't grow. And as I mentioned, that's important. We care about the trend, about the kind of function we have, not about the concrete numbers. And when we talk about the performance of an algorithm, we therefore could say, hey, this solution has linear time complexity, the other solution has constant time complexity. But in programming, we use something which is called big O notation, which simply makes it easier for us to quickly express the time complexity of a given algorithm to other developers. And big O notation looks like this. For linear time, you write O of n. For constant, you have O of 1. Quadratic would be on squared. Cubic would be on with an exponent of 3. And you got other time complexities as well, and you will see them throughout the course. Now we're using this because it's very easy to add this as an annotation in your code, or to tell your interviewer that this solution has a complexity of O of n, so linear time complexity. Big O notation is a super important concept. You'll find it a lot in the internet, and it's the standard way of comparing performance on algorithms. You derive the big O of an algorithm, and then you know O of n is linear, O of 1 is constant, and you know constant is better than linear, for example. So this big O notation plays a huge role and is super important when you're comparing algorithms. Now it's nice that we know about big O. Big O is great, and we care about the function, not about the concrete numbers. Now you just learned that for such a linear time complexity, we would refer to O of n. We would say this solution has a time complexity of O of n, which just means it has a linear time complexity. But the question is, how can we derive this? Because the goal is not that you learn it by heart. The goal of this course, and that's important, is not that you learn about a couple of algorithms and you memorize how to solve them and you memorize their time complexities. The goal of this course is that by the end of the course, you are able to come up with algorithms on your own and you're able to derive the time complexity on your own. And of course, you could always use an approach like we did before, for logging the start and the end time and finding the difference, and then you could try to find the relation. Now, for linear time complexity, that's fairly easy. But for other time complexities, it's hard to see that relation, since you always have to keep in mind that the time you see here is heavily influenced by a couple of other factors. So you can't really rely on it to be very exact or correct, and therefore you might accidentally see a linear relationship where you just have some distortion and you actually have a different time complexity. So using these numbers in the browser is not how you should derive big O and the time complexity. The question then, of course, is how should you derive it? For that, we use a technique which is called asymptotic analysis. And it involves 3 simple steps. First of all, for a given algorithm, you define its function. Now here, I mean the mathematical function you would write to get a graph as we have it on the left. Now, of course, that gives us a new problem though. How do we define that function? How do we know which function this JavaScript function, so this code has, what the mathematical equation for that would be? Now, one important note here. I mean the mathematical equation of its time complexity. So what would be the math function be for a graph as we have it on the right here, which is produced by this JavaScript function? How can we translate this JavaScript function into a math function that produces such a graph? Deriving the mathematical time complexity functions for JavaScript algorithms sounds scary, but it isn't hard. All you need to do in the end is you need to count the number of expression executions. So with that, I mean, you look at your function, at your algorithm, and then you look at each expression, so roughly speaking, every line of code in it, and you count how often that's getting executed. Now, of course, by counting this, you will not get the real time in milliseconds or seconds this function will take. But as I already mentioned earlier, that's not what we're interested in anyways. It's way too unreliable and influenced by too many aspects. Instead, we simply assume that every expression in JavaScript takes roughly the same amount of time. If we then count the number of expression executions, so of code line executions we could say, we can easily compare that number to the number of another alternative function. That's the approach we're going to take here. Now we can have a look at that for a couple of scenarios. Let's account for n equal to 1, n equal to 3, n equal to 10, and then let's see if we can detect a pattern for n equal to anything, so to n. For that, I'll add some space here in the function because that makes annotating it a bit easier. And now let's count, and let's start with n equal to 1. How often does this first expression here execute, where we initialize the result variable? Well, I'd say for n equal to 1, this executes 1 time. When this function, the sum-up function, executes, this line here, let result equals 0, is executed exactly once. Now, how often does this for loop initialization run? And important, I really mean the initialization of the for loop, not the body. Well, for n equal 1, this runs once. We initialize this for loop once. Now, what with the code inside of the loop? How often does that run? Well, if n is equal to 1, then we initialize I to 1, we run this loop, or we run through that body in the loop as long as I is smaller or equal than 1. And if n is equal to 1, that means we execute the body in the loop exactly once. Because after that first loop iteration, I will be incremented to 2. That, of course, is not smaller or equal than n, which is 1, and therefore we'll leave the loop thereafter. And now what about this last expression? This, of course, also is only executed once. Once we make it out of the loop, we run this line. So that's the case for n equal to 1. Every expression in this function runs once. Now what for n equal 3? What about that first expression here, where we set the result equal to 0? Well, this still only runs once. It doesn't matter that n is equal to 3. When the sum-up function runs, this line only is reached once. What about the loop initialization? That also is only reached once. We only execute this line of code once. Yes, we will iterate through that loop a bit more, but the loop initialization, if we want to count it, is only executed once. But what about the loop body now? Well, this does now indeed execute 3 times. Because I is 1 initially, we loop as long as I is smaller or equal than n, and n is 3, which means we loop once, Then we increment I to 2, still smaller or equal than 3, so we loop a second time. We increment I to 3, that is still smaller or equal than 3, so we loop a third time, and only then I is incremented to 4, which means we don't execute the loop again. So that's now a difference. And that last expression is still only executed once, of course, because once we're out of the loop, we execute that line, but thereafter the function is done, we don't run anything else. Now, for n equal to 10, it's similar. The first two expressions and the return statement are each only executed once, but now the body inside of the loop is executed 10 times. And therefore you can of course see a pattern here. For this algorithm, we can say that the only dynamic part is the body in our loop. And the times this body is executed is exactly the same number as we feed into this function here. So therefore, for n equal n, the three expressions here are only executed once, but the content in the loop, the code in the loop, is executed n times. And with that, we can now derive a function. If we want to express the time complexity here with t, then we could say, for the case that n is equal to n, which is of course the case we want to consider because the user is able to feed any number in, then we could say the number of code executions we get for this function is 1 plus 1 plus n plus 1. Now, of course, we can sum this up to 3 plus n, and we could rewrite this as 3 plus 1 times n. 1 times n simply because, well, just n is the same as 1 times n. And you'll see in a second why I'm writing it like this. This is in the end a mathematical function that would describe the number of code executions we have for this JavaScript function. Now, it does not describe the absolute amount of milliseconds or seconds this function takes. But as I said, that is hard to quantify anyways. But if we assume that every line of code execution roughly takes the same amount of time, you could say, if we assume that, then of course we can use such a equation to compare this algorithm to other algorithms. However, we don't even need to be that exact. After all, if you always count all code executions, you have a slower algorithm just by adding an additional line of code in there, right? Because we would have to count that, and therefore we would have a different mathematical function because we added one extra line. But of course, the big picture wouldn't really be changed. That's why we don't have to be that exact, because we don't really care about the exact number of code executions. As mentioned before, we instead care about the general function, the kind of function to be precise, the trend, the growth rate implied by that function. So therefore, when we define that function, we don't need the exact function with the exact numbers. Instead, we can generalize that. And therefore, we could also write a times n plus b. I replaced the concrete numbers 1 and 3 with coefficients, simply because the concrete numbers don't matter. It's the big picture that matters to us here. Which kind of function is this? And this is a linear function. Okay, so now we got the general mathematical function. And no worries, we'll of course see this process of deriving the function and so on for other algorithms in this course as well. So we got this function now. Now, in order to derive this big O notation, we need to find the fastest growing term in that function. And here that's easy. That is a times n, because b is a constant coefficient which doesn't grow at all. It's always exactly the same number. A times n, on the other hand, depends on n, and for a bigger n, that term is bigger. So now that we found this fastest growing term, we remove the coefficient from that term, because again, we don't care about the exact numbers, we care about the general picture, the big picture, the general kind of function. This process here is called asymptotic analysis. Now we narrowed this down to basically this function. We can clearly see that the time complexity depends on n. Well, and that n is simply what you put between the parentheses of the big O notation. That is why it's big O of n. So with our newly gained knowledge, let's now use it to calculate the constant time complexity and see how O of 1 is derived. So here's the sum up function with this one-liner solution, with this mathematical function. And now again, let's count the number of expression executions to find out how often that code runs. So let's look at the n equal 1 case, and let's evaluate that one code expression we got here. How often does this run if n is equal to 1? Well, it runs once. What about n equal 3? Now, you could think this runs 3 times because we use the number n in this mathematical calculation, but that is not how JavaScript and programming languages work. If you have a loop or something like that, then the code inside of the loop is of course affected by the number of iterations. If you add 2 numbers, let's say 100 and 100, this does not mean that JavaScript has to perform a certain execution 100 or 200 times behind the scenes. And here n could simply be replaced with 3. So you would have 3 divided by 2, which is 1.5, times 3 plus 1, which is 4. And this does not mean that it runs 1.5 or 4 times. No, it still only runs exactly once. So this expression here runs once for n equal to 3. And the same is true for n equal to 10 and for whatever value you have in n. And therefore you can see, if you write this as a function, t equals 1. There is no n anywhere in this. When we count the number of executions, we got no expression that would run n times. This one expression we got here runs once. So if we would want to derive big O here, then we would define the function. Well, we did that. It's t equals 1. And here, of course, there is no more general form because there is no n in it. If we find the fastest growing term, that's of course 1. It's not growing at all, but it's the only term we got. And if we want to remove the coefficient, there is nothing to remove. So t equals 1 is our final time complexity function. And as before, we take what's left on the right side of the equal sign and put that between the parentheses of our big O notation, hence we get O of 1. That's how we would derive constant time. Now, just as before, it is worth noting that it doesn't matter if you have any extra code lines in there, right? If we had another console log statement here, of course we would count 2 executions. So our formula would be 1 plus 1. Every line runs once, so we would end up with this equation. What you would do in practice is you would simplify this. So this does not lead to O2, big O of 2, but instead we would still write big O of 1, because we care about the general trend. That's why we focus on the fastest growing term and remove the coefficient here when we have a linear growth function or when we have any time complexity function. Because we don't care about the exact number of code executions in different lines, we want to see the general trend. Here it's linear time complexity, so that t depends directly on n in a linear way. And here it's O1, no matter if you add an extra line of code or not. In the end, what you want to say here, in the constant time case, is that the time a function takes to execute does not depend at all on n. And constant time is of course the best possible case for an algorithm, because it means no matter what you put into an algorithm, it will always deliver the same execution time. It has a constant time complexity, which is of course awesome and highly efficient, but I can already tell you, you will not be able to convert every algorithm to a constant time algorithm. This specific algorithm we had a look at here is an exception, where we have a linear and a constant time complexity alternative. For a lot of problems, you will not be able to find a constant time complexity alternative. But we will see those algorithms throughout the course, and we'll then of course also see different alternatives for those algorithms. Now, just to make this really clear again, we do derive these big O notations to compare different algorithms, because we can't rely on the hard numbers when we measure that, when we measure it in milliseconds or seconds. We can't rely on that. That's why we have this big O notation which tells us which kind of algorithm that is, which kind of time function it has. Now, we learned about constant time complexity and about linear time complexity thus far. For constant time complexity, n, the number of inputs, has no effect on the time the algorithm takes. For linear time complexity, the execution time grows, guess what, linearly with n. So the bigger the n, the longer the execution time, and the factor should be the same. So if you put 10 times as much n into the function, it should take 10 times longer. Now, therefore, we can clearly say that O of n, linear time complexity, is worse than constant time complexity. If we have a look at those charts, we can see the same basically. For O of 1, we always have the same execution time no matter the inputs. For O of n, that's not the case. So O of n is worse than O of 1. As I mentioned before, though, you don't always have the choice. You can't always come up with a solution that has O of 1, as you will also see in this course. Still, that's how these two time complexities are related. And in general, here on this slide, I will order these algorithms from fast to slow. And therefore, let's have a look at a couple of other time complexities you might see from time to time. For example, logarithmic time complexity, which would be written like this, O of log n. A graph could look something like this, and we can see that here, maybe initially it's slower than linear time complexity, but with bigger n's, it tends to be faster because it doesn't grow linearly, it grows at a slower pace instead. So the execution time of the function grows logarithmically with n. For O(n) squared, we speak of quadratic time complexity. A graph might look something like this, and here the execution time grows quadratically with n. So the bigger n, the bigger the execution time, and it grows much faster than for linear time complexity. We have even faster growth, and therefore an even slower algorithm, with exponential time complexity. So 2 at the power of n. Here, this grows even faster than quadratic time complexity, and therefore, since execution time grows exponentially with n, we have a very, very, very slow algorithm, which will quickly be impossible to execute. For very low n's, you will already see problems here. Now, these are not all possible time complexities we have. In theory, any mathematical function or construct is possible. The most common ones are definitely linear, constant, and quadratic time complexity, mixed with a bit of logarithmic time complexity, and in general, as I mentioned a couple of times already, throughout this course we'll see plenty of examples also for different time complexities. Now, however, it's time for you to practice what you learned, because it's nice if I explain all of that. You really need to understand it. You really need to become comfortable with coming up with solutions and judging their quality, judging their time complexity. This is something you need to learn. Now, we will develop this throughout this course, but I already got a nice first practice for you, which you can absolutely solve with standard JavaScript skills and what you learned up to this point. I want you to write an algorithm, so write a function, that takes an array of numbers as input and calculates the sum of those numbers. Then define the time complexity of that algorithm you came up with and check if there is a faster alternative. So find out what the lowest possible time complexity, so the fastest possible algorithm, is for this problem. So if we have a look at the code, you should write some function, some numbers, which takes an array, numbers as input, and which you can call, like you see it here in the second line, and you get back the response, in this case 14, for summing up those numbers. So your task is to write this part that's inside the function and determine the time complexity of your solution, as well as the lowest possible time complexity you're able to come up with. Now for that, attached you find a little starting project, if you want to call it like this. It's a very simple JavaScript project with a HTML file, which is empty, which just imports a JavaScript file, which is also empty. And that's where you should add and call your function. Outputting the result in the console of the developer tools is perfectly fine. You don't need to do anything else. The other files you see here are just for configuring Git and for configuring my editor for recording, so you just find the index.html and the app.js file attached. You can use this as a starting project and add your solution in app.js, and we'll solve it together in the next lecture. Were you successful? Let's solve it together now. And for that, I'll add a function, SumNumbers, which takes my numbers as a parameter. Of course, that parameter name is up to you. And I want to call this with, let's say, an array where I have 1, 3, and 10. And I want to console log the result of the function. So the function should simply return the sum. Now, how could we sum this up? If we knew that the array always has exactly 3 elements, we could return numbers 0 plus numbers 1 plus numbers 2. That would be a valid solution if we knew that we always get exactly 3 elements. Now, the problem is that is not something we know here. When I gave you this exercise, I didn't mention that it would be restricted to a certain length of number arrays. So you can't assume this. Nonetheless, if you could, this would probably be the best possible solution, because this has a time complexity of O of 1, so a constant time complexity, simply because we have one expression here. And for numbers, which has 3 elements, if we assume that it's always fixed to 3 elements, this still only runs once. So this here would be O of 1, constant time. Perfect. Unfortunately, as I mentioned, it's not something we can assume, so I'll leave it here for reference, but it's probably, hopefully, not the solution you came up with. Instead, we don't know how long numbers is. So let's add a result variable maybe, which initially is 0. And let's add a for loop to go through all numbers we're getting. Now numbers is an array here, not a single number. So we can use a for of loop to loop through that. So for every number of numbers, we execute the code inside of the loop. Now the code we execute in here is simply that we add number to our result. And then we return result thereafter. This could be one solution for this problem. If we now save this, and we run this in the browser, I get 14, which is the expected result. Now let's also try it with a different array where I also pass 50 as a 4th value, and we should now get 64 as a result, and that's the case. So our function, our algorithm, seems to work. The question now, of course, is which time complexity does it have, and can we do better than that? Now let's derive the time complexity of this solution, and for that let's count executions. So let's count for numbers being equal to an array with 3 elements. If that's the case, this first line runs once. Right? It's only executed once when this SumNumbers function is called. It does not depend on the length of numbers. This loop here, on the other hand, runs more often than that. It runs 3 times. Now, the loop initialization here actually is only done once, but inside of the loop, we run the code 3 times because we have 3 elements. So our n here is the length of this array, because that's what determines how often this code inside of the loop executes. So that's our n. Now this last line still only runs once because it does not depend on the length of this array. Now if we have a look at this case with 50 as a 4th value, this first line still only runs once, this loop is only initialized once, and this line where we return the result also only runs once. But of course now this code inside of the loop runs 4 times because we got 4 elements, and that is what influences this code here and the number of iterations we have. So if we would want to write this as a function here, we would have 1 plus 1. So this code execution plus this code execution plus this code execution in the last line plus n in the end, right? Plus 4, but if we consider an infinitely long array where we simply have a look at n elements, this would be our dynamic part, because this part here depends on the length of the array, and that is our n in this case. So we could write this as 3 plus n, and as you learned, that is 3 plus 1 times n, if you want to write it like this. So this here would be our time complexity function. Now you learned that as a first step, we should then find the fastest growing term, and that definitely is this part here. So we would simplify it to that. And then we would remove the coefficient, so the 1, so we're left with t equal n. Now, as a side note, if you had an extra line in there where you console log something, you could, of course, count this extra line, and this would execute 4 times as well. But the only difference would be that you, in the end, would write plus n, right? Because you have 2 n's now, basically. So you have 2n here, 2 times n. Hence, you simplify this to 2 times n, you remove the coefficient, and you got the same result. That's what I meant earlier. It does not matter if you add an extra line. It's about the general big picture. So therefore, we would write this as O of n, and that, of course, is linear time complexity. That's the time complexity we got here. Now, the question is, can we do better? Now, generally, that's, of course, not that easy to answer. You probably don't know all possible solutions to all possible problems. But let's dive into that code. Is there something we could improve? Now, for that, of course, we should focus on the part of our code that depends on n, because we can't improve this first line or this return statement. It runs only once, so there's no way of improving that. But if we could get rid of that loop, we would certainly win a lot. But to be honest, for this problem, if we don't know the length of the array in advance, there really isn't a way of getting rid of that loop. There really isn't a way of shortening this here. Now, of course, you could get rid of that for loop. You could get rid of that implementation we have here. And you could instead return numbers reduce using the built-in reduce method that comes with JavaScript essentially, where reduce takes a function, for example, an arrow function, where you then get your sum and the current number you're looking at. And you initialize the sum with 0 with that second argument you passed to reduce. And inside of that function, you return sum plus cur num. With that solution, if I save that, I still get 64 as a result. And now we have a one-liner, which is, as we learned, just big O of 1, constant time. So we won, right? It's better. Yeah, not really. This is something you could think, and if that was your thought process, I can't blame you, but it's not entirely correct. This here calls a new function, right? Now before, when I showed you that magic function for adding up all numbers, we had one mathematical equation that was n divided by 2 times n plus 1. Now, we're not calling a function here. We have a mathematical equation here, which is solved by JavaScript. Here, we are calling the reduce method. And the reduce method, internally, will do something similar as we're doing here. So reduce will not really turn this into a big O of 1 solution, because we make our function shorter by relying on another built-in function. But that doesn't make the built-in function faster. And that's an important takeaway. Just because you were able to shrink your code down to one line does not make it a constant time code. That's only true if in that one line you're not calling a new function. Here we are calling a new function, the reduce method. So we would have to look into that reduce method and find out what its time complexity is to derive the time complexity of our function here. Now, you could do that, but in the end, I can tell you reduce will also give us linear time complexity, so this is not an improvement. Indeed, this solution we had before, where we have a simple loop where we go through all the elements, that's our best possible solution in the end. That has linear time complexity, and for this problem, we can't do better than that. And that's what I also mentioned before. You will not always be able to get a constant time algorithm. Sometimes you just have to live with linear time complexity, like in this case. Sometimes you have to live with an even worse time complexity. So here it's linear time complexity, and I hope I could make clear how we derive this and why it is the best solution here. So now we already had a quite nice introduction into the basics of algorithms, the very important topic of time complexity, and therefore I now want to give you an overview of what's inside this course in general and what the course goal is. Because this course is not an algorithm practice book. It's not full of hundreds of algorithms through which we're going to go, but it isn't that because I find it much more important that you are put into the position that you're able to solve problems on your own. You need to be able to come up with your own solutions, with your own algorithms. And this course has the goal of giving you a foundation for that. Therefore, we'll of course thoroughly look at the what and why. I already gave you an introduction to algorithms, and throughout this course we'll always come back to this key question: why are we doing something? How does something work? What is the approach here? We'll see a bunch of examples. Just because this course isn't a practice book does not mean that we're not having a lot of examples. We do, but we'll see a lot of examples on different algorithms, different kinds of algorithms, and also, very important, different solution approaches. So different ways of solving algorithms, but also some repetition so that you have a chance of getting a feeling for a certain way of solving something, so that you have a chance of understanding how to tackle certain problems. We'll have a look at recursion, at something which is called dynamic programming, at greedy algorithms, and more. The overall goal of this course is to give you one core thing: a solid foundation and a plan on how to tackle and solve problems. Now, I want to be very clear. By the end of this course, you will not be able to solve any problem that is out there in just 5 seconds. This is not how it's going to work. Instead, this course will lay out a foundation on which you can build up on to then practice on your own, to dive into more algorithms and to understand what you're doing there, so that finally, after practicing and with help of this course, you are able to solve problems, to ace interviews, and to do whatever your goal is. I want to be very honest here, because no course can just give you that knowledge. You need to develop it on your own, but for that, you need a solid foundation, and that is what this course will give you. Now, in detail in this course, we have all those basics, and we learned about time complexity in this first module already. And that is one of the most essential parts you need to know to get started with algorithms. Now, of course, getting started is nice, and we need those essentials, but we also want to apply them. We want to dive into concrete examples. Therefore, in the next module, we'll explore math algorithms. We'll explore algorithms that have something to do with numbers, with mathematics, and where you will already dive deeper into these core concepts and be able to utilize what you learned in this first module. Now, as a next step thereafter, I'll introduce a very important concept, and that's recursion combined with dynamic programming. You'll learn what dynamic programming is and why it's extremely important when we're working with algorithms, when we're tackling problems. Now, with that new tool, with that new knowledge gained, we'll explore search algorithms and sorting algorithms, two very important categories of algorithms which you'll need in real life a lot. And we'll thereafter explore a different metric besides time complexity, which I can already say is the most important one, but besides that, we'll then also explore space complexity. Now, with that, and with all that new knowledge you gain throughout these modules, we'll dive into sets and array algorithms. Sets essentially are arrays, we could say here, and you will learn how that all works and which tricky problems we might face there. After that, we had a lot of practice, we learned a lot of key concepts, and will therefore then dive into more complex algorithms. For example, the problem outlined at the very beginning of this module, and I'll give you a blueprint, a plan for solving problems and for deriving algorithms. Now, one important note here though, it might be tempting to just go ahead and dive into that last section, or just dive into the sorting algorithms section because maybe you just want to learn sorting algorithms. This is not how this course works, at least. There might be other courses which simply are practice after practice after practice. This course has the clear idea of building up a strong foundation that you have at the end of this course. And therefore, I strongly recommend that you go through the sections in order. And if you do jump ahead, be prepared to face concepts or solutions which you might not fully understand or where you need to do your own research. So my strong recommendation is that you go through the sections in order, and then by the end of the course, you will have that strong foundation on which you can build up on. In the first module of this course, we had a look at big O notation and what algorithms are and how we judge algorithms and their performance, which is super important because often you will need to decide which algorithm is the better alternative for solving a certain problem. Now, in this module, we'll dive into more algorithms. Specifically, we'll have a look at a bunch of math algorithms. We'll have some fun with numbers here, and we'll do that for two main reasons. First, of course, I want to show you more examples, more algorithms you might need as a developer or you might face in interviews. But of course, the overall goal is that we can explore more algorithms, but that you also get a better feeling for big O notation and for how to solve problems. Because that's the ultimate goal of this course. And this will be a progress. This is something you learn by doing. You will need to get better and better at judging the performance of an algorithm, so of deriving the big O notation. And of course, it's also the goal that you get into the right way of thinking about such problems. And again, that is simply something that comes with experience and by practicing. This is not something you can or you should learn by heart. It's simply a step-by-step process, and therefore, let's dig deeper into that and let's explore some math algorithms. We'll start with a very popular example, a very popular math problem, and that's the Fibonacci sequence. Now, what's that? This sequence in the end looks like this. Though it's an infinite sequence, it doesn't end, hence the 3 dots at the end here. And in the end, it's a sequence of numbers that starts with 2 ones, typically, and where every other element in that sequence, for example, the 89 here, is simply the sum of its 2 preceding elements. That's how this sequence is built up. So 2 is the sum of 1 and 1, 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, and so on. That's how this sequence works. Now, what's the idea behind this sequence? Why does it exist? It's not an invention by programmers or by people working at Google who want to have nice interview questions. Instead, it's a real math thing. As always in life, on Wikipedia, you can learn more about that Fibonacci number or sequence. And in the end, there you'll learn more about its history. One important place where this is applied, or where you see this in action, so to say, where it's coming from in the end, is this Fibonacci spiral. In the end, that sequence, if you square the numbers in it, you would be able to create a spiral like this. You could derive a spiral like this, and that in turn is a spiral which you often find in nature. You can see an example here. Now, a deep dive into this would be something for a math course or a math class. And we'll therefore just take it for granted. We have this idea of this sequence, and we'll now simply take that sequence and see what we can do with it. Because here's a popular interview question you might be getting. Return the nth element of the Fibonacci sequence. So that means if you had a function fib, which should do that, which should solve this problem, and you passed in 4, this function should return 5, because 5 in that sequence is the element at index 4. So here I'm implying that nth starts at 0, that we're talking about the index of the element here. Now fib of 4 should of course always yield 5 because the sequence is always the same. The sequence is not impacted by the input number to that function. That function should just return an element from that sequence. So therefore, if we want to solve this problem, we want to work with that sequence, we have to come up with an algorithm that does 2 things. The first thing is that we need to calculate that sequence, but only up to the element we're looking for. Since the sequence is infinite, there is no way we can calculate it in total. It's infinite after all. So we calculate it up to the element we should retrieve in the end. And then we return that element. So that's in the end what our algorithm needs to do. Now, definitely think about this problem, see if you're able to come up with some solution to that on your own. You won't need any fancy math skills for that. You just need regular JavaScript knowledge. In the next lecture, we'll solve it together, and we'll then of course also have a look at the time complexity of our solution. So how could we solve this problem? For that, I'm back in a simple project where I just import app.js, which is an empty JavaScript file. And in there, let's write a function fib, which takes the element we're looking for, so the position of the element we're looking for as an input, and which then should return that number we're looking for. And then here we can simply console log fib4 and maybe fib5. Now, inside of that function here, of the fib function, we have to do those 2 things I outlined on the slide. We have to build that sequence, and then we have to return the right element. Now, let's start with building that sequence. For this, we can create an array, numbers, whatever you want, and we can initialize this array with 2 elements, 1 and 1, because these are our 2 starting elements in the Fibonacci sequence. Then we need a loop to add more numbers to that array. However, of course, only as much numbers as we need to reach this nth position. So here I'll add a for loop where we start with I equal to 2. And I set I to 2 here because the next element I want to add has the index 2 in the end. So we use I here as the index we want to add. So as the element at the index we want to add. We have indexes 0 and 1. We now want to add a third element, which will have index 2. Hence, we start at that. Then we want to keep on looping as long as we're smaller than n plus 1. This is our running condition, our condition to keep this loop running, because when I is equal to n, then we, of course, have the index. We're working on the index we're looking for here. So then we can stop and return. And then we simply increment I by 1 here. And inside of that loop body, we can now push a new element onto the numbers array. And that new element will now be the next element we add here, so the element at index 2. And therefore, we're looking at the element directly in front of it and the element 2 places in front of it. And we'll add those 2 things together. So we take the numbers array here and access an element dynamically, the element at index I minus 2. So 2 elements in front of the one we want to add. We want to add a third element here, so we need that one 2 places in front of it. So 1 place, 2 places, so this 1 here for the first iteration, as our first number, which we add then. And we add that with a second number, which is I minus 1, so which has the index I minus 1. This should now make it clear why we start at I equal to 2. Because we use that index we're working on, the index of the number we want to derive, as our starting position, and then we deduct 2 to take the element 2 places in front of it, and we deduct 1 to take the element directly in front of it, and add those 2 numbers together. So for this first iteration here, where we just have this numbers array initially, this here numbers I minus 2 will refer to this one. And this part here, numbers I minus 1, will refer to this part. We add those together, hence this here yields 2 for the first iteration, and therefore we push a new number 2 into this array. That's how this works. And then we return numbers at the index we're searching for. We can do this because we know after this loop, we will have an element at this index because of our exit condition. So therefore, if I try this again, accidentally deleted my old console log here. So if I console log fib4 and fib5 and I save this, if I reload here, I output 5 and 8. And if we keep in mind that this Fibonacci sequence was 1, 1, 2, 3, 5, 8, then it makes sense that for index 4, we return 5, because here we have index 0, 1, 2, 3, 4. And for index 5, we return 8 because that's this one here. The next element in line would be 13. Now, of course, in this algorithm here, we only generate a sequence that is as long as we need it to be, and not a single digit longer. If I console log numbers here before we finish, you'll see that numbers ends with the number we're searching for. Otherwise, our algorithm would be inefficient if we would generate more than we need. Because we only want to find the element at this index, there is no need to generate a longer sequence. So therefore, that's what we're doing. This is my solution for the Fibonacci sequence here. It sounds like a complex problem. If we have a look at the solution, it's not too difficult though. Now, chances are that when you first encounter something like this, you struggle with coming up with a solution like this. In the end, it is just plain JavaScript though, and it really is all about practicing those things. The more algorithms you write, the more you get into this way of thinking, the easier it'll get. Now, let's analyze the time complexity of that solution in the next lecture. What's the big O of this function? What's the time complexity? Well, you learned how that works. Let's count our expressions and how often they are executed. Let's start with the expression in this line with this statement here. This is executed once for every function call, no matter which n we pass in, because if n is 10, we still only create the array once. The same for the return statement. We only return once per function call, so this is also 1. Now what for this loop? We initialize it once, but inside of the loop body, this code here, of course, runs a bit more often. How often does it run? Well, it runs almost n times, but not entirely, because we don't start at 0 here. Instead, we can log how often it runs. We can simply log running here, or anything else, and then do this for fib4, let's say. And if we now reload, you see 3 times. And that's, by the way, a nice way of finding out how often code in a loop runs. If you're not sure about it, just add a console log statement in there and let the browser count it for you. Of course, you could also create a helper variable, counts, which is 0, and then you simply add 1 to that for every iteration, and then you log that once you're done. Then you don't have to count multiple console log statements, but you just get the count like that instead. This also works. Now, either way, we see it runs 3 times. So, put in other words, since I fed in 4 as a number, we could say it runs n minus 1 times here. So what's our time complexity then? Well, we could write it as 1 for this line, plus this line, plus this line. So 1 plus 1 plus 1 plus n minus 1 in the end. That's how often it runs here in the loop. Of course, this would change if I add a console log statement here in the loop, running. Then this line is also executed n minus 1 times. So we would have to write 2 times n minus 1 back here, because we have 2 statements in the loop that are being executed. And if we do that, we have basically 1 plus 1 plus 1, so 3 plus 2n minus 2 in the end if we calculate this here. So ultimately we have 1 plus 2n. But in the end, that doesn't matter too much, because as you learned, you thereafter simplify this. You look for the fastest growing term, which is this one here. So we can simplify this to 2n. And then here you remove the coefficient. And therefore we get just n, and that's our big O then. So here we have O of n. And that's, of course, linear time complexity. So in the end, the performance here depends on n, and the bigger our n is, the longer we take, but we have a linear dependency, we have linear time complexity. This algorithm uses O of n as a time complexity. Not too shabby. Now, of course, the question is there a better alternative? Now, you can definitely think about that. For example, we could look into options where we use recursion here, but that's something we'll do a little bit later in the course. I can already tell you that with recursion, we won't get a better result. But at the moment, we don't really know how to calculate this with recursion. So therefore, we'll not do it at the moment. We'll just stick to this solution because indeed, there really isn't a better way of solving this. You can't do better than linear time complexity here for this algorithm. And linear time complexity in general, by the way, is not too bad of a result. Often you are quite happy if you find an algorithm with linear time complexity. With the Fibonacci sequence, we had another example of an algorithm, and therefore another opportunity for you to practice this problem-solving thinking and that big O notation. Now, let's simply have a look at yet another algorithm, yet another problem we can dive into. Because, as I mentioned, the more we practice, the easier this all will get. So now, let's have a look at the so-called primality test and what that is. The primality test is all about determining whether an input number is a prime number. So if we would call a isPrime function that should contain that test, we would get false for 9, which is not a prime number, and true for 5, which is a prime number. And just to make sure we're all on the same page, a prime number is a number that's only divisible by itself and by 1. So 5 in this example can only be divided by 1 and by 5, and not by any other number. Now, of course, you could divide 5 by 2 and you would get 2.5 as a result, but we speak of prime numbers if the result is basically an integer. So if the result does not have any decimal places, that's why 5 is a prime. 9, on the other hand, is not a prime number because we can divide 9 by 9 and by 1, but also by 3. And we then get 3 as a result, which is an integer. So that's how prime numbers work. Again, a math thing. And we can, of course, write a function that checks a number and finds out if it is a prime number or not. Now, an algorithm that does that, so the content of this isPrime function, essentially needs to do one thing, therefore. It needs to try dividing that number by all smaller numbers, you could say, and return true if it in the end is only divisible by itself and by 1. Now, again, try this on your own first. Try coming up with a function that achieves this result, that takes a number as an input and returns true if it's a prime, returns false otherwise. In the next lecture, we'll do it together, and again as before, we will of course then also check the time complexity of that solution. So back in this project, I saved the Fibonacci example in a new file, and the app.js file is therefore empty again. And in there we can add a isPrime function. Now, what should we do in there? Well, first of all, we get a number as an input, the number we want to check, so that then we can check for isPrime 5 and isPrime 9, for example. Now, what do we need to do inside of this function to return true for this case and return false for this case? Well, in the end, we want to try dividing this number by all smaller numbers. And basically, if we find one number by which we can divide where the remainder is 0, we know that it's not a prime number. Because normally we shouldn't find any number by which we can divide if it is a prime, because a prime number is only divisible by 1 and by the number itself. So if you find any other number by which we can divide, where we then have a remainder of 0, so where we get a number without decimal places, where we get an integer number as a result, we know that it's not a prime number. So therefore we can write a for loop here where we start at 2. We don't want to start at 1 because every number is divisible by 1. So the first number by which we want to check dividing is 2. And then we go up to number as long as we're smaller than number. We don't want to check number itself, so we don't have smaller or equal here because we'll always be able to divide by number. And we exclude 1 and dividing by number because that would be our prime conditions. And then we increment I. So we simply go through all the numbers smaller than numbers starting at 2. And now we do something simple. We have an if check in there, and we check if number modulus I is equal to 0. The modulus operator divides number by this number and gives us the remainder of that division. So 5 modulus 2, for example, would yield us 1. Because 2 fits into 5 2 times, and then we have a remainder of 1, because 5 minus 4 is 1. And you can simply check that in the JavaScript console to get a feeling for this operator. So if that returns 0, which it, for example, does for 4 modulus 2, because 2 fits into 4 2 times, and we have nothing left, if it returns 0, we know that the division is possible with an integer as a result. And that tells us that we don't have a prime number here. So therefore, if this condition is true, if we make it into this if check, we return false, because our function is called isPrime. So if we can make a division, we don't have a prime number, hence we return false. If we make it through all those numbers, so after the for loop, and we never returned, we know we didn't find a single number by which we could divide where we would get an integer as a result, and therefore we then return true because we then have a prime number. That's my algorithm here. If I now save this and I reload, I get true for this first console log statement, and that makes sense because this indeed is a prime number, and I get false for the second one, which also makes sense because 9 is not a prime number. So this algorithm seems to work. Now let's analyze it, let's check the time complexity and see if we can find a better alternative. So what's the time complexity of this? As always, let's count expressions. This line here will only run once. It actually won't even run all the time, but I'll come back to that. But at most it runs once. It won't run at all if we return earlier. This for loop is initialized once. This if statement is evaluated once. However, actually also not always. If we check isPrime for 1, for example, you will see that we get true, which is correct, but you will also notice that this if check here is never reached. If I add console log running here in the loop, you will see that running never prints before we return this first true result. And the reason for that is that we never make it into this for loop if our number is 1, because we start at I equal 2, and we only run as long as I is smaller than number. So that simply means that for number equal to 1, and also equal to 2, by the way, we'll never make it into this for loop. That's just a side note. So this if check does not always run, but if we make it there, this runs once per loop iteration though. So actually, that would be n times, right? If number is our n, then this would be initialized n times, assuming that the number here is bigger than 2. Now, the line inside of the if statement does certainly not run n times. This runs at most once, because thereafter we're done anyways. We don't always make it into this if check after all. So we always check this if we make it into the loop, but of course we don't always have a true condition. So this line does not always run. So therefore, evaluating this is a bit more complex here, as you can tell. To be precise, we have different cases which we might want to have a look at. Now, I'll have a closer look at that later when this matters even more. But we already have an example here with the primality test where we have different cases with different time complexities. We often have that for sorting algorithms, and we have a whole section on sorting later, but we also have that here in this primality test algorithm that we're working on. So in such cases, be that the case here or another case where we want to sort the numbers in an array from small to big, we might have different cases. Let's stick to the sorting example for now because it's very easy to understand. Let's say we have the best case, that the input array, if we want to sort this array, is an array that already is sorted. In that case, our sorting algorithm, depending on which algorithm we use, more on that in the sorting section, might have a time complexity of O of n. It checks every item, it sees that the order is correct, and it doesn't need to do more. However, we also might have a worst case, where we have the inverse order. So we need to swap all those elements. We need to change that entire order. And it turns out, depending on the sorting algorithm you're using, that here you might have a time complexity of O(n) squared. Again, why we have that complexity is something we'll dive in later in that sorting section. For now, let's just take this for granted, because I just want to focus on the fact that we might have different cases depending on the input values. So therefore, what we typically do when we judge time complexity is, we might have a look at the best and at the worst case, but we care most about the average case. And the average case in the case of sorting would be that we have a random order. We, as the developer writing the algorithm, we don't know which values we'll get. So we assume it'll be random. And then we care about the time complexity of that, which in this case also would be O(n) squared, but more on that later. Now, in interviews, you might be prompted to also specify the best or worst case time complexity. And in some real problems you're working on, you also might care about those best or worst case complexities, because maybe you have parts in the application that you can optimize to more often get the best case in other parts of the app. But in the majority of cases, you will care about the average case because you can't predict which other case is more likely. Now, one important note about the average case here. You will see throughout the course that often when I refer to the average case, we in the end have the same result as in the worst case. For one, because for a lot of algorithms that actually is true. There is maybe some best case scenario available, but if you can't tell which inputs you're going to get, you often end up with the worst case automatically. But in addition, it's also hard to really quantify the average case. It's hard to really determine the average case and how an algorithm performs. Therefore, when we judge algorithms, we tend to focus mostly on the worst case, and often the average case is derived from that worst case. And only in some scenarios we are able to really identify a separate average case, which we then can judge. Therefore, for the majority of this course, you will see that the average case is actually pretty much the same as the worst case. In rare circumstances, we do have a separate average case, but as mentioned, we mostly focus on the worst case. Additionally, an advantage of focusing on the worst case is that we're prepared for the worst. We can judge how bad our solution might be in the worst case. And if the actual reality then is better, well, that's great. We take that for sure, but we can't assume that it's going to be better. So we simply plan for the worst and hope for the best, you could say. The most important takeaway, however, just is that you sometimes have different cases. And typically, you can tell that you will have different cases if you have if statements here, or if you have different starting or ending conditions in your for loop. Like here, when we start with I equal to 2, that of course means that not all input values will be reflected in the loop. But the if statement is the best indicator for different cases you might want to have a look at. And that explains why it is a bit strange to derive the big O notation here. We know that the content in the loop runs for most numbers, but not for all. And we know that this return statement is reached only once and only in certain conditions. So which different cases would we have here? Well, if the number is 1 or 2, then we have the case that the for loop never runs. So if I log running here again, and I log the numbers 1 and 2, and not 9, you will see that we don't have a running here in the console, because we never make it into there. So that, of course, means that for 1 and 2, we have a constant time complexity. So we could say here our best case is that number is equal to 1 or number is equal to 2. In that case, we would have O of 1. Because we never make it into the for loop, we only run this line, and that is constant time that always takes the same amount of time. Now, the worst case is, of course, that we pass in a very large number. If number is something like 1,000,000 or even more, then of course we make it into this for loop because it's bigger than 2, and then we run this for loop like 1,000,000 times. Now the actual worst case is not just that the number is big, but that it's also a prime number, which 1,000,000 of course isn't. But if it is a prime number, then we also never make it into this if check. So we therefore complete this for loop all the way up to that number we passed in, and then we run this last line. And therefore here we have a complexity of O of n, linear time complexity, because we have one for loop and we go through all the numbers up to the number we've fed in. So we have n iterations basically. Not entirely, it's n minus 2 we could say, but that doesn't really make a difference, and we therefore would simplify this to O of n as you learned. Now that's the worst case, and I want to make it clear that for 1,000,000 it's not really the worst case, because for 1,000,000 we can already see that we can divide it by 2. So we actually will cancel this for loop if we check this for 1,000,000 already after the first iteration. So if I log this for 1,000,000, you will see that we only see running once here. Because we start at 2, we immediately are able to divide 1,000,000 by 2, so we immediately finish. So 1,000,000 is not a bad case actually. But if we had something like 72,277, which is far smaller than 1,000,000, we'll actually have a problem. If I use this number here and I reload, you see this takes long. I have a lot of iterations here, as you can tell. I actually have 27,277 minus 2, and therefore 27,275 iterations, because it turns out that this number, 27,277, is a prime number. So that is a real worst case. We never make it into this if check because we find no other number by which we could divide. And therefore we go all the way up to that number in that loop. And therefore here we really see that it takes a very long time, right? It took quite some time for this to finish here. And that's the case because we didn't exit out of this earlier. So that's a true worst case, a big prime number. And in such a case, we have linear time complexity because we execute the loop for all numbers up to that number. So we have O of n in that case. So that's how we can think about this. What's the average case then? Well, the average case, of course, is that we don't know the number, that it's probably not 1 or 2, but that it's also not necessarily always a big prime number. So sometimes it's a big prime number, but sometimes it's also just 8, which is of course not a prime number. So we don't know the number. And what's our time complexity then? Well, that would also be O of n. Because it's only in 2 cases O of 1, that's our best case, we can't assume this here, and for all other cases it has a linear dependency between time taken and the number fed in. Of course, if we feed in 1,000,000, we're done after 1 iteration. For other numbers, we need a bit more iterations, even if they're not a prime number. And for some numbers, we need a lot of iterations for the big prime numbers. So therefore, we have a tendency to take as long as the number we feed in. In most cases, in the vast majority, we'll not take exactly the number of iterations as the number we're feeding in. Sometimes that happens in the bad cases, but not always. But we'll definitely also not just take no or one iteration. That's why we approach this linear time complexity and we have O of n. You could say O of n down there is far worse than here, but if we would have to describe the time complexity, since we don't know the number in advance, we would have this average case of linear time complexity. And this, of course, is just an approximation. You can't calculate this because you don't know the numbers the user is going to feed in. You just analyze the different cases here and you make an approximation, therefore. And that's why we have the very bad case where we have O of n, but where the average case also has a tendency to have that time complexity, even though in most cases it will finish faster than in the worst case. Now we had a look at the primal t-test, at the big O notation, and at the different cases there. And that case thing is something we'll see again and again. It can be confusing at first, but like this overall algorithms thing, it is something that gets easier with practice. Now before we move on to a different algorithm, let's revisit the primal t-test algorithm though, because we can actually improve it and find a better alternative. O of n, which is the time complexity we currently have, is not the best possible time complexity we can achieve here. Now to understand how we can improve this, let's have a look at two examples. 5 is a prime number. It's divisible by itself and by 1. And 9 is not a prime because besides by itself and by 1, we can also divide it by 3. Now, the thing is, every number that's not a prime, like 9, has a product that consists of two factors a and b. So in the case of 9, that would be 3 times 3. That's what makes it not a prime number in the end. We can have a division like this, which does not include the number itself and which does not include 1. So both factors a and b, in this case 3 and 3, are neither 1 nor the number itself. And that's true for every non-prime number. Now the thing is, if we split it into factors like this, there is a simple rule you can observe in the end. At least one of those factors, sometimes also both, like in this case, is smaller or equal than the square root of the number you're analyzing. In this case, the square root of 9 is 3, and in this case, both factors then are smaller or equal, in this case equal, than that square root. And that's simply a rule that's true for every non-primal number. At least one of those factors will be smaller or equal than the square root, because if both factors would be bigger than the square root of the number you're looking at, the multiplication of those factors would yield a bigger number than the number you're looking at, which just can't be the case. And with that in mind, we can rewrite this is-prime algorithm to actually make it a bit more efficient. Instead of going all the way up to number here in our for loop, we can go all the way up to math square root of number. The math object is built into JavaScript, available in the browser. Square root is a built-in method, and it generates the square root of number. Now, that square root, in the case of 9, would be 3. And the result is that we have far less loop iterations here. In the case of 9, we only iterate up to 3. And the result is that for the big numbers, so in the worst case, we have far less loop iterations. For the good cases, not much changes. But in the bad cases, since we can abuse this fact that we know that at least one factor has to be smaller or equal, for those big numbers, we simply save a lot of iterations by only going up to the square root. So in this case, where we have that iteration with 27,277, where we previously had a lot of iterations, 27,275 iterations, if I now reload, you see we only need 164 iterations. So that is much, much faster. So with this improvement, we can actually improve this worst case a lot. Now instead of O of n, we have O of square root of n in the end. as our approximate time complexity function. Because we know that we will definitely never take n iterations, n code executions in there. We'll never need all 27,000 and something code executions. We know that we definitely will need at most square root of n or less code executions. And therefore, that's not just our improved worst case, but also the improved average case. Because we know that we never will need more than the square root of n iterations, because that's our loop exit condition in the end, and that's what drives our time complexity. So here, with some extra math knowledge, we could find a much better result. Now, chances are, and that's totally fine by the way, that you didn't come up with that, because it's not something you necessarily have in your mind, that that's the case for primal numbers and that we have a rule like that. And that's not necessarily an issue. If you're working on a real project that needs optimization, you have Google. As dumb as it sounds, you can use Google to find alternatives, to find math rules like this. In an interview situation, the interviewer might simply point you towards this solution if you just think about it. If you say something like, well, currently we go through all those numbers for a big prime number, maybe we can use some math to shrink this, and then maybe you get some help to derive a solution like this. So you don't need to learn this by heart. You never need to do this for algorithms. You just always need to be open to consider alternatives, to consider possible improvements, and therefore to, like we did it in this case, possibly improve your algorithm and make it much, much faster. And that's why I wanted to show this to you. Now you could add more optimizations. You could, for example, check division by 2 and 3 before you actually go into that for loop, and therefore rule out a lot of common division operations. You could do that, but it wouldn't really impact the time complexity. In some cases you would be faster, but in the worst case you wouldn't be faster, and therefore, since the average case is mostly driven by the worst case, the average case also wouldn't really improve. Nonetheless, below the video you find a more elaborate version of this algorithm, which has all possible improvements included, which therefore would be the fastest one, theoretically, but which still would have O square root of n as a time complexity for the average and the worst case. So we saw two new algorithms in practice, and we also learned about cases. Now, as I said, experience comes with practice, and therefore it is now time to practice what you learned and practice to work with algorithms in general. Here's your task. I want you to write two algorithms which will actually work independent from each other. The first algorithm should take an array of numbers as input and return the minimum value in the array, so the smallest number you find in that array. The second algorithm, which has nothing to do with the first one, should take a number as input, so not an array, just a number, and return true if it's an even number or false if it's an odd number. Now, besides those algorithms, those functions, you should also define the time complexities for those two algorithms, so find out what the time complexities are, and also have a look at possible cases you might have there. That's your task. Definitely try it on your own first. You need nothing more than what you learned. Then, of course, definitely compare your solution to mine, and of course also do so if you're not able to come up with a solution here. No worries, there will be plenty of other opportunities to practice this in this course. So I'm back here in my project, got a new app.js file which is empty, old code is in the is_prime.js file, and in there I will now solve those two tasks of the assignment. And let's start with task number 1, which was to come up with an algorithm, with a function that gives us the smallest number in an array. Hence, I'll create a function, getMin, something like that, and there I expect to get an array of numbers as an input. Now in there I want to return the smallest number I find in there. How could we do that? Well, I would say we definitely want to have a look at every element in the array and then find out if it's the smallest one. So we will definitely need a loop. And here I'll just have a loop where I go through all my numbers with this for off loop. Of course, you could write a different loop as well, but that should do the trick. And this will now walk through all the numbers in the array. Now, the problem is to find out if a number is the smallest one, we need to compare it to the other numbers in the array. So what we could do is we could add another loop in there. And for every element in the array, we have a look at all other elements in the array. We compare it to those other elements. And we therefore find out if there is a smaller number. So here I could have my other num array where I also go through numbers in the end. So I have a loop in a loop. And in there I have an if statement. And I check if num is smaller than other num, let's say. And if that's the case, I know it's smaller than at least one other number. Not necessarily than all other numbers, just smaller than one other number at least, which is not really the result we need here. So that might not be what gets us there. Now, there might be a way of getting this to work, but since we want to find the smallest value in the entire array, maybe we don't need a loop in a loop to compare it to individual other elements. Instead, maybe we just need one loop where we go through all the elements, and we need a helper variable, current minimum, something like this. And initially, we set that equal to the first element in the array we're getting. Side note, this will not work if the array is empty, so you might want to add an if check and check if the array is empty, and if that's the case, return. But here I will just assume that it is an array with at least two elements. So we then initialize current min to this first element in the array, and then we go through all elements in the array. And now in this for loop, we just need an if check, where we check if the number we're currently looking at in that loop is smaller than current min. So if it's smaller than the number which we previously identified as our smallest number. And if the number we're now looking at is smaller than that, we know that this number is our new current min. So in this if check, we set current min equal to num, because now we got a new smallest number. So current min might change a couple of times, but by the end of the for loop, once we're done, we know that current min will definitely be the smallest number. Because imagine we pass in an array of 3, 1, 5 here to get min. In that case, we would initialize current min to 3 here in this line, and then we would go through all elements. First of all, we would have a look at 3 again, because we go through all numbers. And we check if 3 is smaller than our current min, which is also 3. That's of course not the case, so we don't go into that if block, we just continue to the next iteration. The next number we have a look at is 1. Now 1 is smaller than current min, because current min is still 3. So now we're in the if block, and we now set current min equal to 1, our new current min. Then we continue to the next number, so to 5, and we check if 5 is smaller than current min, which is now 1, which of course is not the case, so we don't make it in there. Hence we finish here, and we return current min. This should do the trick. This would be a getMin function. Let's now give it a try. Let's call getMin and feed in an array 1, 2, 3, which should of course return 1. Then maybe 9, 8, 3, 5, 1, which should also return 1. And then maybe also 10, 3, 8, 8, 6, something like that. This should of course return 3. If we save that and we reload here, we see 1, 1, 3, which is the expected result. So this algorithm seems to work. Now let's analyze the time complexity and possible cases we might have here. So for that, let's again count operations. This first line here runs once, no matter how many numbers we feed in. This line executes once. If we feed in an empty array, it actually will not work, but as I said before, we just assume that we always have a working array here, let's say at least 2 numbers. So this runs once. The loop is initialized once. The code in the loop, so the if check here, runs multiple times now. It runs as often as we get numbers. So this would be n. The more numbers we get, the more often this code in the for loop runs. So we have n in here. Now this last statement here runs once. We return always once. And what about the code in the if check? Well, that now is again an example of different cases. Now, for every if check, it runs once, but in the context of this loop, of course, it might run multiple times. And we actually have different cases here. We have a best case, we have a worst case, and we then have our average case. Now let's analyze different cases. Best case would be that our smallest number is the first number. Let's say 1, 2, 3. That here, that's the best case. Because in such a scenario, we initialize current min to 1. We still go through all numbers, but we don't make it into this if check at all. Because we already have the smallest number as current min, so no other number is smaller than that. So this never executes for the best case. However, for the worst case, where we, for example, have 3, 2, 1, so exactly the opposite, this executes much more often. For the worst case, our current min initially is 3, and then we go through all numbers. And for the first iteration, we look at 3, which of course is not smaller than 3, so we don't make it in there. But for the second iteration, we look at 2, which is smaller than 3, so we make it in there and set a new current min. And for the third iteration, we look at 1, which is smaller than 2, so we again make it in there. So here we have n minus 1 in the worst case in the end. So this runs twice to be precise for this example here with 3 elements, which is n minus 1, 3 minus 1. So 2 times for this example in the worst case. Now the average case, what would be an average case? Well, 2, 3, 1 could be an average case, or 2, 1, 3, so we don't know. So for the average case, we don't know. For this example here, it would run once. So again, that's just true. This 1 is just true for this exact example here. Because for this example, current min initially is 2. So for the first iteration, we don't make it in there. For the second iteration, we look at 1 though, which is smaller than 2, so we make it in there. So that's 1. For 3, we don't make it in there again, so in that case we would have 1. But that's just this specific example. So long story short, for the best case, we have n iterations here. The if check still runs n times, don't forget this. We still go through all numbers. We just don't make it into the if check all the time. For the worst case, it's also n. We also go through all numbers there, and the only difference is that we execute this code a couple of times. But since that is inside of the for loop, that doesn't really matter. The for loop is still executed all those times, so the asymptotic analysis gives us n here. And for the average case, it's therefore also n. So it's O of n in all cases, even though the exact amount of operations in the if statement is different. But for the loop, we always have n iterations, and if we apply the asymptotic analysis we learned about, in the end we get O of n in all cases here. And that's the time complexity of getMin. Now let's have a look at the second part of the practice assignment. There, you should write a function isEven, which would return true for an even number and false for an odd number. So here we get a number, not an array, but a single number as the input. And we want to return true if this is even and odd otherwise. So how could an algorithm for that look like? Well, it can be a simple one-liner. We can return the result of this expression here. Number modulus 2 equal to 0. Now the modulus operator, as I explained earlier, will give us the integer remainder of a division. So 5 modulus 2 would give us 1. 4 modulus 2 would give us 0. So therefore, if we compare the result to 0, we'll get true if we have no remainder, which is true for even numbers. And we'll get false if we do have a remainder, which is true for odd numbers. So here, if I console log is even for 2, and for 4, and then for 7, we should get true, true, false. If I reload, That's what we get. Now, what's the time complexity of that? Let's again count. This line here, the first line, executes once, always once, no matter which number we feed in. And we have no loop in there. We have nothing of that kind. We're also not calling a different function or method in there. And therefore, indeed, that's all we have here. This is constant time. And we also have no different cases here because we have no if statements. We have no for loops with different starting conditions. We just have one line. So we have one case here. And there we have O of 1, constant time complexity. So this is a very, very simple algorithm. No cases, constant time complexity, the dream of every developer. And that's another example. The key takeaway, besides the concrete algorithms maybe, should be how you get there and how you think about time complexity. And the more and more we progress into the course, the less and less I'll start writing formulas as I did it initially. Because the more you work with those algorithms, the quicker you see that, for example, this algorithm is O of n. We don't need to derive this by writing 1 plus 1 and then finding the fastest growing term. You can already tell we have a for loop there, we have nothing else that would make it more complex, so this is O of n. It's as simple as that. We can then have a look at different cases and see how the for loop behaves for different inputs. But in this case, since the for loop executes through all numbers for all possible array combinations we could provide as an input, we also got O of n for all different cases here. And that's really how you should think about it. Don't start writing long formulas. Those change anyways if you add an extra expression here. Instead, really just see the general patterns in your algorithms and be aware of those cases. I hope this exercise made this a bit clearer, and with that, let's continue. Now, thus far in this course, we already saw a couple of algorithms and a couple of different time complexities. I also showed you this asymptotic analysis approach that allows you to derive the time complexity of an algorithm on your own. And we most often saw something like O of n or O of 1 thus far. Throughout the course, we'll also see a couple of other time complexities, of course. Now, there are two important takeaways here. The first important takeaway is that we're really only interested in this asymptotic analysis. We're only interested in the big picture, in the nature of an algorithm. We don't care if it theoretically is O2n or O3n or anything like that. For us, it's interesting that it's O of n, so that there is a linear relation between n and the time this algorithm takes. And it doesn't matter to us how steep that linear graph would be. It doesn't matter to us if the runtime grows twice as fast as n or anything like that. We just care about the general trend. That's the first important thing. But in addition, you also should reach a state where you don't need to count all operations, but where you simply look at a function like this and you quickly see which kind of time complexity we have here. It's of course good if you're able to identify best and worst cases, since that is also something you should be capable of doing. But more importantly, you should be able to relatively quickly see what the worst or average case runtime is, what big O notation we would use. And there are a couple of very easy rules, or at least hints towards which time complexity we have for which kind of algorithm. Thus far, we mostly saw O of n and O of 1. We also had O of square root of n, but that is kind of similar to O of n, just a bit more specific than just O of n. But these are the two general kinds of time complexities we saw thus far. O of n, as you learned, is linear time complexity, which means a higher n leads to an increase in runtime, and the increase in runtime is linear. And O of 1, on the other hand, means that the runtime is not really affected by a higher n. Now, to quickly identify which kind of time complexity which function or algorithm has, there is a simple rule. You typically have a O of n kind of algorithm if you find a single loop in there. With single loop, I mean that an algorithm could have multiple loops, but no nested loops. For example, here for getMin, we quickly see that there is a loop in there. Now, if we had a second loop after this first loop, we would still have linear time complexity, just something like 2n or anything like that. If we had a nested loop in there though, so a loop in the loop, then I can tell you it will not be linear time complexity, then it would probably be quadratic time complexity, but we'll see this later. So a loop, a single loop without any nested loops, is a great hint towards linear time complexity. On the other hand, if you have a function without any loops and without any other function calls inside of it, there is a very high chance you are dealing with constant time complexity, like down there. So these are two easy rules which are easy to memorize. Have a loop without any nested loops, and of course also without any nested function calls, so without any function calls inside of the function, then you're dealing with linear time complexity most likely. Have a function where you have no loop and no nested function calls, then it most likely is constant time complexity. Now cases like our isPrime function here, our isPrime algorithm, where we actually had O of square root of n, there, the square root part is nice to have. Of course, it's more specific than just O of n. But if you would say that this algorithm is O of n, it would also not be horrible. We just can be a bit more specific here. So the takeaway here simply is that if you have a loop, it most likely is linear time complexity. But it then is worth taking a closer look at that loop to see what's going on in that loop. And you should check how your iterator, your exit condition variable, changes with every iteration, and what your exit or your runtime condition is. And if you then see something strange, like that you shrink that number up to which you loop, or that you don't just add 1 to the iterator after every iteration, but you add a bigger number. If you have something like this, chances are you're better off than linear time complexity, because you won't go through all the numbers up to a number, but you instead shrink the number of iterations you're going through, simply by changing the exit condition and or by how you manipulate I after every iteration. So that's the second step. The first step is that you look for loops, and then if you have a loop, as a second step, analyze that loop and see if there is something strange about it that influences the number of iterations and maybe decreases that number so that you're not on linear time, but you're better than that. Let's dig into one more algorithm before we'll then have a look at an alternative way of solving some problems, of implementing some algorithms. Here we'll use nothing too special though, nothing too fancy for this problem. And this problem is called is_2. The goal is to determine whether an input number is a power of 2 or not. So if we would call that function that has our algorithm in it, and this function would be called is_2, then this function should return true for 8, which is 2 at the power of 3, but it should return false for 5, which is not a number that can be calculated with 2 at the power of something. So our algorithm needs to make sure that we produce that result. And therefore we could say we write an algorithm that does one core thing. It divides the input number, 8 or 5, and all future division results it produces until 1 is reached. And then we check if the remainder is always 0. So if we basically were able to make that division by 2 without ever producing some remainder. Because if we do produce a remainder, like when we try to divide 5 by 2, that doesn't work. We can't produce just an integer there. If we use the modulus operator on 5 divided by 2, we would get 1 as a remainder. So if we do get a remainder, we know this number can't be divided by 2, and therefore it can't be calculated with 2 at the power of something. And if we get such a remainder for any division, then we know this will not work. Now this might sound very abstract, so therefore let's simply implement this together, and then I'll also show you one super nice smart trick with which you can shine in any interview. So here I'm again in an empty app.js file, and in there let's implement this isPowerOf2 function. It gets a number as a parameter, and the goal is that we can call it isPowerOf2, let's say with 8, and here we should get true as a result. For 5 we should get false, for 16 we should get true, and for let's say 13 we should get false. That's the idea. Now how can we write this? I had a verbal description on the slide, but that might have been a bit difficult to grasp, so let's simply implement it step by step. Well, first of all, we can check if the number we're getting is smaller than 1. If that's the case, we can return false because we know that won't work. We can't divide this by 2. It's certainly not at the power of 2. This also rules out negative numbers to be fed in. You could of course omit this if you know that you get a number that's at least 2 as an input. So let's therefore now have a look at the core of this algorithm. For that, I'll add a new variable here, divided number, and initially that's just my input number, but we're going to change this variable throughout a loop. And now here we could add a for loop and make it work with that somehow, but I will actually use a while loop here and basically check if divided number is not equal to 1. And inside of the while loop, I will then change divided number and will gradually approach 1 there. So how will we do that? Well, we take divided number and we set this equal to divided number divided by 2. So we divide this number by 2, and we do this inside of a loop, so this divided number gets smaller and smaller. If we feed in 8 to this function, we'll set divided number to 8 initially, then we go in the while loop, and we divide it by 2. So now we have 4, which is not 1, so we continue. In the next loop iteration, we divide 4 by 2, so we have 2 in divided number then, which is not 1, so we continue. And then we go again into the loop, and there we had 2, we divide it by 2, now we have 1, that's our exit condition, and we're done. Now of course we'll have a problem if we feed in 5 though. With 5, we have divided number equal to 5. We go into the loop, we divide it by 2, so now we have 2.5. And in the next iteration, we divide 2.5 by 2, which is 1.25, which is not 1. So we go into a new iteration, and we divide 1.25 by 2, which is a number smaller than 1. So this exit condition will not be met, and we would have an infinite loop, and we would continue dividing that number, and we would approach 0 therefore. We would get closer to 0 with every iteration. We would never reach 0 though, and we therefore in the end have just an infinite loop, because this exit condition in the end is never met. We never have equal to 1, so we never would make it out of this loop. And therefore we need to add a if check here. And we need to check if divided number modulus 2 is not equal to 0. And that if check simply makes sure that if we feed in a number that can't be divided by 2 anymore, we know about that, and we have a way of reacting to that. And in there, I will return false, because if we ever make it into there, we know the number we fed in originally, when we started dividing it, eventually reached a point where we can't divide it by 2 anymore without creating a number that has a decimal place, so a non-integer number. And if that's the case, we know we certainly can't have a number that can be produced with 2 at the power of something. So that makes sure that we return false eventually. If we make it past this while loop, we on the other hand know that we have a number that is 2 at the power of something, otherwise we would have made it into the if check at some point. That's how this works. Now it's not enough to just generally check if the number that's fed in can be divided by 2 without producing a remainder, because consider the case that we feed in 20. This can be divided by 2, so if that would be our only check, if we hadn't the code down there, then we would be able to divide 20 by 2, and we might return false here, but return true here therefore. So since we can divide 20 by 2, we would not make it in there, and we would return true. And we would indicate that 20 can be constructed with 2 at the power of something. But that would be wrong, because 20 can be divided by 2, and so can the result of that division, 10. But the result of that division, 10 divided by 2, which is 5, cannot be divided by 2 anymore, at least not without producing a number that has a decimal place. So that means that whilst 20 is divisible by 2, it can't be calculated with 2 at the power of something. And therefore we need this more elaborate solution where we don't just check the input number, but also all the results of divisions by 2. And therefore now we derived a function that hopefully gives us true, false, false, true, false as an output. Well, let's check this. And that is the case. True, false, false, true, false, as expected. So this is an algorithm that allows us to determine whether a number can be calculated with 2 at the power of something. And I hope I could make it clear why we need a solution like this, and why just checking for divisibility by 2 is not enough. Now, what about the time complexity of this algorithm? Now, that's a bit more tricky. For one, we got different cases, of course. For the case that we get a negative number or a number that can't be divided by 2 even once, so that would be our best case, something like a number equal to 13. We basically have constant time, because for such a number, for 13, we make it into this loop once, we immediately see that we can't divide it by 2, and we return false. But the worst case is a bit more tricky. The worst case would be a large number that can be divided by 2, like a million. If we check a million manually here in the terminal, we can divide it by 2 and we get 500,000. We can take 500,000 and divide this by 2. We can take the result of that and divide it by 2, and so on. We can do that for quite some time. But then at some point here, in this case for 15,625 divided by 2, we get a non-integer number. And this is where our while loop would finish. So if we have a look, we had 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, 7 steps here for a million. Now that's not too horrible, right? That's pretty okay. So what is our time complexity therefore? Of course, for bigger numbers that are divisible by 2, but that are not 2 at the power of something, we take a couple of runs through that while loop, but will still be done relatively quick. So we don't have O of n here. That's not what we have here in the worst case, because we're far away from the n, from 1 million iterations. So instead, what we typically would have here is something like log of n, a logarithmic time complexity function. If you think about this slide again, I had a look at logarithmic time complexity there as well. And if you look at this chart, you see that of course it grows, but for big numbers it doesn't grow a lot. Very large numbers like a million or 10 million are almost on the same time level as smaller numbers like just 100 or just 1,000. So we just have a relatively steep curve at the beginning for small numbers, but very quickly we approach a relatively constant time complexity for algorithms that have such a logarithmic time complexity. And a good way of getting a feeling for that and for seeing that is that we don't count operations manually, but we add a couple of console logs so that we get those operations counted for us. For that, I'll just paste the function here in the browser. Of course, we could also edit it in our app.js file, but I'll add it here, and inside of that while loop, I'll now add a new line, console log, executing, just like this. And now we can call this function for various values. I'll just clear the console. The function is still there, just not visible anymore. And now I'll call is power of 2 for, let's say, 3. And we see executing once. Now let's call it for 900,999. Still, only once. Now that's our best case, of course. Let's now call it for 8. Here we see 3 executions. Now let's call it for 16. We see 4 executions. Now let's call it for 1,000,000. And we see 7 executions, so far away from 1,000,000. Now, even for large numbers that ultimately are a power of 2, will not take too long. If we quickly derive such a number with the built-in math power function, let's say 50, which is quite a large number, even if I take that number here, you see we only have 50 executions here. So far away from whatever that number is, iterations. So you see, I can add bigger and bigger numbers, but the number of executions doesn't grow even close to as fast as those numbers are growing. And that always is a great indicator for logarithmic time. Even if you don't calculate it mathematically, which is hard here, since we also have different cases, just by exploring the nature of this algorithm and running this calculation with a couple of demo numbers and logging each execution to the console, just with this approach, which is a fine approach of analyzing the time complexity, we are able to tell that we certainly don't have O of n here. Otherwise, that number would need to be much closer to that number. And if you have something like this, where the number of operations grows, it's not constant, but it grows at a much slower pace, then you typically have logarithmic time. That's a typical example, and that's how you can derive that with console logs and by simply thinking about the nature of this algorithm. Now, with that newly gained knowledge coming back to our code here, we actually have to correct our worst case. It's not 1,000,000, it's actually a big number that is a power of 2, because that is where we will take the most iterations. So something like that large number we derived here in the console a second ago, something like that number, that is the actual worst case, because there, for this exact number, we saw that we would take 50 loop iterations. Now actually this also allows us to refine our time complexity judgment here. Log of n is fine, you could say it has O log of n, but of course since we here always talk about a power of 2, we know that for such a large number, which is an example for our worst case scenario, we have basically the power of 2 iterations. So here we took 50 iterations, and that was just what we used as a power for this calculation. So actually we have log 2 of n. That means logarithm at the base 2 of n. That would be our actual time complexity, but we can also simplify this to log of n here, and that will be fine as well. The nature of this algorithm is important, and the nature that matters to us here is that we take logarithmic time. You don't have to be mathematically super correct. You need to find out what the general time complexity is and why it behaves the way it behaves. So I'll stick to that. That would be our updated worst case though, because that is even worse than just a random big number that is calculated as a power of 2. That is where we will take most iterations. Now, I did promise you that there is a little trick we can use for this power of 2 problem that would actually lead to a more elegant or shorter solution. We can use some bitwise magic. Okay, what's that? Well, in JavaScript, like in pretty much all programming languages, you can also do bitwise calculations and number manipulations. And to be honest, it is something most developers don't really know, and I would include myself into that, to be honest, because I don't use that regularly. But here we can use a nice little trick, and that's not something you have to know by heart for an interview. It is just something, if you do keep it in mind, if you can remember it, it's a great bonus point for sure, but otherwise it won't be a problem. Now, to understand the approach we're going to use, we have to understand how decimal numbers are reflected in the binary system. If we have unsigned numbers, so non-negative numbers, here 1, 2, 4, which are of course numbers that can be calculated with 2 at the power of something, we would represent them in binary form like this. 1, 10, 100, or to be precise, 1, 1, 0, 1, 0, 0, and so on. And you can simply use a decimal to binary converter to determine something like that. So here, for example, if I enter 4, I get this binary number. If I enter 8, you see there's an extra 0 at the end, and that's a pattern that continues for numbers that are 2 at the power of something. We simply add an extra 0 at the end. On the other hand, other numbers like 7 look totally different in binary notation, if you want to call it like that. Now, we can use that in our algorithm. We can use a bitwise operation to check if a number is power of 2. And for that, we use this bitwise AND here. Now, this is not the logical, the Boolean AND you might know. That would be 2 ampersands. No, here we have 1 ampersand symbol. And this does something different. So before we write any algorithm, let's understand what this single AND does. So what does the bitwise AND operator do? Keep in mind that a 4 in binary notation is 1, 0, 0, 0. 8 is 1, 0, 0, 0. Now we can also write 0, 1, 0, 0 for 4, and then 1000, so 1, 0, 0, 0 for 8. This here is also still 4. You can add leading zeros, they make no difference. Now what the AND operator does is it compares those different digits to each other. And it then generates a new number based on that comparison. And the comparison works like this. It compares the first digit of the first number to the first digit of the second number. And it always compares that in binary notation. And for 0 compared to 1, it would give you back a 0, because you have at least 1 0 in there. For 1 compared to 0, you therefore also get 0, and for 0 to 0, you also get that. So the bitwise AND would produce this new binary number. Now it does that binary stuff behind the scenes, you use it with decimal numbers. But you get back a 0 because of that behind the scenes work it does, which I just explained. Now let's have a look at a different example. We saw that a 7 converted to a binary number is 111. So if we compare 4, which is 100, to a 7, which is 111, we would get a different result. Now for this comparison, 1 compared to 1 would yield us 1, and then the other two comparisons would yield us 0 each. So we get back 100 in binary notation, and we know that this translated to decimal should be a 4. And indeed, if I compare 4 to 7 with the bitwise AND operator, I get back 4 because of that behind the scenes work. Now, why am I explaining this to you here? Because we can leverage that combined with our logic we have on the binary presentation of numbers that are 2 at the power of something. I did show you that 2 is equal to 10 in the end, 4 is equal to 100, 8 is equal to 1000, and so on. So if we would add leading digits to make sure they're all 4-digit here, we see we always have just 1 1 in those numbers at different places. So if we compare those numbers with each other, if we compare 2 to 4 or 4 to 8, the result will always be 0, 0, 0 because we never have a 1 in the same position. That's just a hard rule for the binary numbers behind 2, 4, 8, 16, 32, and so on. So that's something that's good to know, because this allows us to come up with a formula that will always return true for a number that is 2 at the power of something and false otherwise. And that formula is the number we want to check, and with the bitwise AND, the number minus 1. And if we try that for 4, for example, so 4 and 3, we get 0. If we try this for 8 and 7, we also get 0. So we will always get 0 for this formula if the number we're checking is 2 at the power of something. And for other numbers, this does not work. So 7 and 6 would give us a non-zero number. And that's a simple rule you can derive, and that's a rule we can utilize here now. In app.js, we can rewrite this is power of 2 function here, and hence I'll comment it out, to be much simpler. Is power of 2 for a given number, and all we do in there now is we still check here if we have a negative number, because it won't work for negative numbers. But with that checked, we have a one-liner. We just return number and that's a bitwise and, number minus 1 if that's equal to 0. So we return true. If that is equal to 0, we return false otherwise. And with that, let's just put this between quotes so that this is evaluated all in the correct order. With that, if we save that and we reload, we get true, false, false, true, false, but now with a one-liner. And of course here we were able to reduce time complexity. Now we basically have O of 1 because we only have this one-liner which always takes the same amount of time no matter which n we feed in. So this is a better alternative. Now still, I'm totally aware of the fact that this is not necessarily something that came to your mind. And to be honest, it didn't come to my mind neither. This is something you find if you search on the internet, if you search for alternatives. And in an interview situation, you might not be asked for this algorithm anyways, because it's not one of the most common ones to be asked for. But even if you are, it's totally fine if you don't come up with this solution here. The vast majority of interviewers will not expect you to know this because very few developers really know about these bitwise operators and how to use them. Now, I just give you the knowledge here to score that extra bonus point if you should get it though. If you don't remember that in an interview though, it's not a problem at all. I just want to show you this nicer approach of solving this. Also, to really show you that you can be very creative when it comes to coming up with alternative solutions. Sometimes it's an easier loop you can write, sometimes it's a mathematical trick you can use, and here it's a kind of mathematical trick we're using. Here we're using binary notation and bitwise operations. So, nice to know, not something you need to learn by heart, but something I did want to include here so that you have this extra knowledge at hand in case you should need it. You might remember that slide. I talked about the nature of an algorithm, which you should detect a few lectures ago. It is important that you don't always have to manually count operations, but that you have a couple of things to look for, like loops and then the exit condition or the change of the iterator in the loop, so that you're quickly able to identify the big O notation, the time complexity of an algorithm. Now we learned about logarithmic time. There, the runtime does grow, but it doesn't grow at a similar pace as it does with linear time complexity. Linear time complexity means that if you add 1 to n, the runtime also takes 1 unit longer. Logarithmic time complexity simply means that if you add 1 to n, the runtime takes longer, but it doesn't grow linearly. The time it might take longer is a very small fraction that it takes longer. So there is no linear relation between n and the increase in runtime. And you typically have such algorithms if you have an algorithm where you have some kind of logic, for example, inside of a loop, where the number, where n is split into smaller chunks. So that's something you might want to look for. Like in this case, we're splitting the number we're going through by 2 in every iteration. Keep in mind that divided number is part of our loop condition here. So if we change the divided number, we of course affect the number of iterations we need, since the number has a direct impact on the number of iterations. And if we split it by 2 in every iteration, it's of course relatively easy to see that we're not dealing with a linear time complexity here, because big numbers quickly become very small if we divide them by 2 in every iteration. And if we then use that divided number in our loop condition, well, we're certainly only dealing with a relatively small amount of iterations. So if you have something like this, where you split your exit condition number or your input number into smaller chunks in every iteration, then you're typically dealing with logarithmic time. Because if you split a number, even a big number becomes a small number relatively quickly. So therefore, things like that are something you should watch out for when you're looking at an algorithm, because splitting your number, splitting your data you're running your operation on into smaller chunks as part of a loop is a clear indicator that you're having logarithmic time complexity. Now in this module, we had a look at a lot of math-related algorithms, we had a look at a lot of time complexities, and we really analyzed a lot of algorithms already. Now, not all algorithms are about math. We got plenty of other interesting things like searching arrays for items and so on, and we will cover that in the next modules as well. But these math algorithms allow me to lay out a nice foundation, explain the core concepts, and in addition, of course, you sometimes have math problems you need to solve, or you might be getting asked for such math algorithms. Now, to conclude this module, let's have a look at the factorial algorithm, because this then also allows me and us to have a nice transition to the next section, which will be related to that. But let's start simple. The goal is to calculate the factorial of a number. So if you would call your function with that algorithm, the result for calling it with 3 should be 6, for calling it with 5 should be 120, because the factorial of a number is simply the multiplication of the number with the number minus 1, with that number minus 1, and so on. And therefore, our algorithm in the end again needs to do one core thing. It needs to go through all smaller numbers of a given number and multiply them all with each other. And of course, with the input number itself as well. That's the goal of this algorithm. Now, as always, definitely try this on your own first. Here's a short pause for you to pause the video, and thereafter we'll implement this together. So, let's do this together now. For this, I'm back in an empty app.js file again, and in there, I'll add my fact function. Now, this fact function takes a number as an input, and now in there, we wanna, well, calculate the factorial. The goal is that we're then able to call fact with 3 and with 4 and with 5 and, well, get the respective outputs. And of course, therefore, I should console log them. So let me quickly do that. Console log the results. And let's now work on that fact function. Now, this function can be very, very easy. We simply add a loop where we go through all the numbers leading up to this number, and we then multiply them with each other. Therefore, I'll add a helper variable, result, which initially is 1. 1 because we're multiplying, not adding. So if I would set this to 0, and I then start multiplying this with something, we would always get 0. That's why we start with 1 instead. And then here in the loop, a regular for loop, I start with I equal to 2, because I could start with 1, but multiplying 1 with 1, well, is still 1, so it doesn't make too much sense. And I then go through all my numbers up to number including number. Hence, the condition is smaller or equal, because the number itself should also be multiplied with result. And then we simply add 1 to I after every iteration, and result is equal to result times I. And since we go through all numbers from I equal to 2 to I equal to number, we multiply result with all those numbers. And then we return result. And this is already it. This is a function, an algorithm, deriving the factorial of a number. If we give this a try and reload, we get 6, 24, 120 as a result therefore. And this makes sense because this is 3 times 2 times 1, so that is 6, of course. Here we got 4 times 3 times 2 times 1, so that is 12 times 2 times 1 is 24. And here we got 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1, still 120. That's our result, and our algorithm works. Now, we did this multiple times, and this one will be an easy one. What's the time complexity here? Well, we could start counting operations again, but by now you should already be able to see what the nature of this function is. And you see that we're essentially going through all numbers up to a number, and therefore here the time complexity simply is O of n. It's linear time complexity. The bigger the number we're feeding in, the longer this takes. We're not dividing number by anything. We're not taking the square root. We're not having anything like that. It's a simple O of n algorithm here. So that's it. That was a fairly trivial one. I did show this algorithm last because now in the next section, I will show you a different way of writing this using recursion. And when we use recursion, things can get interesting when we talk about algorithms. So back to our factorial function. Here, factorial.js has the factorial function as we wrote it with a regular loop. Now, let me be very, very clear. There's nothing wrong with this function, nothing wrong with this approach. This is perfectly fine. You can absolutely use this approach. But we could also write it differently. We could write it differently using recursion. For that, in app.js, I'll re-add my fact function that takes a number still. And I still have my expected outputs down there, so I'll copy that over. But now inside of the function, we're going to do something different. In there, we're going to write this in a recursive way. And that simply means that this function, the fact function, will call itself from inside the function. That's what recursion is all about. If you call a function from inside that same function, we're talking about recursion. So here, we would simply call fact number -1, for example. We're calling the fact function from inside the function. That is valid in JavaScript. That is valid in most programming languages. And this will work. But of course, this will create an infinite loop, because all I'm doing here is I'm calling this function again with number -1. And then in that function call, I do the same, and the same, and the same, and the same. And we would have an infinite loop. So don't run this. This crashes your script in the end. It's an infinite loop. So therefore, you always combine recursion, at least recursion that should not create an infinite loop, with a so-called base case, with a exit condition. Here we would check if the number we're getting, if that is equal to 1. Because if we get 1, we know we don't need to call this function again. Instead, I just return 1 in this case, because the factorial of 1 is just 1. Now, what do we do down there? What's the idea behind using recursion here anyways? Well, if you have a look at the factorial here, what you can see is that the factorial for 3 is 3 times 2 times 1. So it's 3 times the number -1 times that number, 2 minus 1, and so on. That's what the factorial is mathematically. That's how it works. So therefore, we could write a function here that simply calls itself again with number -1. And therefore, we calculate more and more results. Ultimately, when we reach 1, we return just 1. We don't call ourselves again. And then we're able to resolve all those function calls that we stacked up in the end, and we derive the overall result. And that's in the end the goal here. If number is not equal to 1, and we're simply expecting numbers that are greater than 1, therefore, we return number times number -1. So for 3, for the first function call, we have 3 times the same function for 2. And then in that function call for 2, which we just started, we have 2 times the same function for 1. For that function call for 1, we return 1. So for that function call for 2, we get 1 here as a result. We had 2 times 1, so we return 2. And that brings us back to the initial function call for 3. There we had 3 times fact of 2. That now returned 2. So now we overall have 3 times 2. We return 6. That's how it works. And hence, if I save that, that already is all. If I go back and reload, we get the same results as before. Now, if it's unclear how that works, definitely check out the courses I recommended. You can always use the developer tools there, dive into your source code, and place a breakpoint there. And then reload. And then you're able to step through those different function calls. And the call stack here in the bottom left corner is simply the number of ongoing and paused function calls you have. And the deeper you venture into this, the more function calls you stack up until you eventually return 1. And once you do that, you go through that call stack from top to bottom, you return the results to the individual function calls, and ultimately you're therefore done at some point, and you return the overall result. That's how recursion works in the end. But again, I do have my courses that dive deeper into that if you're interested. So therefore, we can write this factorial function, this factorial algorithm, also in such a recursive way. Exactly as we just did it, either checking for n equal to 1 or smaller or equal to 1 here in the base case, doesn't matter too much. And then with our recursive step, which in the end builds up that number over time. And as I explained, you can think of this just like a chain of function calls. For fact4, we would return 4 times fact3. That gives us 3 times fact2 in that function calls, 2 times fact1, and that ultimately returns 1, and that's simply then passed up, and therefore overall we get 24 in the end here for fact4. That's how recursion works. And we can use this in algorithms as well. But how do you now derive the time complexity of that and judge if that's better than the loop-based solution? Well, we can again count operations, but of course that's made a bit harder because we have a nested function call in there. Let's still try it. This here runs once, this runs at most once. This line here also just runs once per function call, but of course we have a new function call in there. So we kick off a new function call here. And hence, all this code runs again, and possibly again. And we can see how many function calls we need on this slide. For fact4, we execute the function once for 4, a second time for 3, then a third time for 2, and then one last time for 1. So we have 4 function calls for fact of 4. We have 5 boxes here because I have the initial code where we call fact4, but it's the 4 boxes on the right that are kicked off based on that, which are our individual function calls. Now, in every function call, we have constant time, right? We got no loop in there. So in every function call, we have O of 1. That's what we counted there. But we trigger multiple function calls. To be precise, n function calls. And therefore, our time complexity is n times O of 1, and that simply is O of n in the end. And that's the same time complexity as we had it for the loop-based solution. So this is not faster, but it takes less code, and that could be a decision factor as well. This has the same time complexity, just written in a different way, and for recursion like this, you can simply count the number of function calls, and then look into the function and see which work you're doing in there. And as I said, we have constant time complexity in every function call, but we're doing that n times, and n times constant is simply O of n. Because if you're not liking this notation, you could have also written this as 1 times n, and then if we remove the coefficient, we have n, so we get O of n. That's in the end how we derive this. So this is the time complexity here. You can simply count the number of function calls and derive the work that's done in each function call. And with that, you're also able to use recursion in algorithms. Now, we will see algorithms throughout this course that use recursion because they then produce better results than alternative solutions. And there, you will also have a hard time counting all function calls. Therefore, you will learn about a different way of judging the performance or the time complexity of recursive algorithms later. But for a lot of algorithms, this approach here will work just fine, as you see. Now, recursion looks nice. We often can write less code to solve a problem, but I can tell you, recursion is not always better. It's not always the best solution. And for that, let's have a look at a recursive implementation of the Fibonacci sequence, which we already had a look at in the math algorithm course module. There, we used a plain loop to build up an array of numbers where we then return the nth element, and that gave us linear time complexity. The bigger the number is we feed in, the longer it takes, but the time it takes grows in a linear way. That is how we solved the Fibonacci problem before. This, by the way, is also called the bottom-up approach because we're building up our solution from the bottom. We're building up that array from the bottom up to the point we need it, and then we return our value. Now, that was a totally fine approach, but let's now see how we could do this with recursion. The recursive function for the Fibonacci algorithm could look like this. We get our n, or our number, whatever you want to name it, and we first of all check if n simply list to type, so I'll stick to that. If n is equal to 0, or if n is equal to 1. So if we're trying to get the first or the second element in that Fibonacci sequence, and since I start at index 0, the first element is n0, second element is n1. If you want to get one of those first two elements, we return 1, because you learned the Fibonacci sequence is an array that starts with 1, 1, and then we start adding more and more values here. That is how it worked, right? That's how the Fibonacci sequence works. So that is kind of our base case here, and now we can add a recursive step. For that, we call our function again from inside the function with n-1, and we add another function call with n-2 to that. Because in the end, that's how we derived this sequence here, right? We have a new number that is simply the number 2 places in front of it, n-2, plus the number 1 place in front of it, n-1. So if we feed in, let's say, 3 here, we want to get the fourth element because our index starts at 0. So we want to get 0, 1, 2, 3, this element, the 3 here indeed. Well, therefore, we would simply not make it in here because we have n3, not 0 or 1. And then we would execute our function for n-1, so for 3 minus 1, which is 2, plus same function execution for n-2, which is fib of 1. So these two functions will then be kicked off and will do their thing, which of course for most numbers will involve that they also trigger new function calls. But eventually, once all those function calls resolve and the result bubbles up, so to say, and comes back to this main initial function call, each of these two functions here will return a value, and then those values will be added together, and this main function call, in quotes, there is no such thing as a main function call, but this function call that started everything will return that overall value eventually. That's the idea how we can leverage recursion to solve this Fibonacci problem. If we try this, and if you try this, use a small number, you will soon see why. So if I try this for 4 and 5, and I then reload, I get 5 and 8, which are the expected numbers in my sequence. 4 is index 4, so 0, 1, 2, 3, 4. That was 5, as expected. 5 is index 5, so the next number in line, that was 8, and that were our results. So this works. What's wrong with it? Well, what's wrong with this approach is that when we call it, we in the end build up such a tree of nested recursive function calls here. In the end, we have a couple of nested function calls. For 4, we call fib3 and fib2 inside of that function. And inside of those functions, we call fib2, fib1, or fib1, fib0, and maybe even more nested function calls. And this, of course, doesn't look too good. We add more and more function calls for relatively small numbers already. In addition, you can see we have kind of repeated function calls. fib2 will always produce the same result. Nonetheless, we're calling it multiple times here simply because it's in different branches of this recursive tree here. Now, for this example here, we have 9 function executions. We call fib4, fib3, fib2. You can simply add it up. It's 9 boxes which I have in this tree here. So we have 9 function executions for the number 4. Now this gets worse. For fib5, this tree would look like that here. A lot of nested function calls, 15 executions, even though we just increased fib4 to fib5, so we just increased the number by 1. Nonetheless, we went from 9 executions all the way up to 15 executions, so we added 6 extra executions for a number increase of 1, so from 4 to 5. So the number was only increased by 1, but we added 6 extra executions, and we got more repetition here. A lot of repeated blocks of code in that tree. And that gets even worse if we go from 5 to 6. So again, we only increased the number by 1. Nonetheless, the tree now looks like that. And I don't even mark the repeated blocks. You will see a lot of repeated branches, a lot of repeated function calls in there. And here we have 25 code executions. So we go from 9 executions for fib for the number 4 to 15 executions if we just increase that number by 1 to 5, to even 25 executions if we increase it again by 1 from 5 to 6. So we add more and more executions for every increase in the number we feed in, and that's a problem. So what would be our time complexity of this recursive function? It's probably not O of n, which was the time complexity for the loop-based solution. There we had O of n, but what's the time complexity here? Well, we can of course count. As mentioned multiple times, we got 9 executions for 4, got 15 for 5, got 25 for 6. So if we increase the number we feed to the function by just 1, we have an exponential increase in executions. It doesn't grow in a linear way. It's not like the number goes from 5 to 6 and we have 1 extra new execution. No, in this case, from 5 to 6, we go from 15 to 25, so we have 10 extra executions. And that was a bigger increase than we had from 4 with 9 executions to 5 with 15 executions. So the number of executions we add seems to grow the bigger our n gets, and it grows in an exponential way. Now, I'm not talking about O(n) squared, about quadratic time, because if we had a quadratic time complexity, that would mean that if our n is, let's say, 6, we would simply have 6 times 6, 36 operations if we had quadratic time. And if we then go to 7, we would have 7 times 7, so we would only add 13 new operations here. Now, the problem is that this doesn't seem to be the kind of growth we have in our function here. Because if I check this for different n's, for different numbers, you see the growth is moderate. Of course, we go from 16 to 25 to 36 to 49, but the jump isn't as large. Now, I can tell you, it just doesn't fit on a slide. If we would go from fib 6 to fib 7, we would not just add 10 or 12 new executions. No, we would pretty much double the amount of executions here. So quadratic time is too slow. We're not growing with quadratic time here. I can tell you that our algorithm here actually has exponential time complexity, O of 2 at the power of n. So not quadratic time, that would be n at the power of 2, but 2 at the power of n. Because the bigger the number is you feed in here, the longer it will take. Now, how do I derive this, though? Well, for one, you could simply test it for bigger numbers and see how many operations you're getting. But you can also have a look at the function. And what you see is that for every function execution, we start 2 new function executions, right? We have this return statement where we have 2 recursive calls in the end. So since we start 2 new function execution for every execution, that's exactly this exponential growth. We introduce 2 new function calls for every function call. So every function call then again spins up 2 new function calls, and that quickly explodes and gives us a lot of ongoing function calls. And that's what we call exponential growth, when the growth basically accelerates itself, you could say. And that's exactly what we have here. And you will relatively soon find a number where this actually crashes your browser. If I try this for 35, and depending on your machine, you might not want to try this, you will already see that this at least is not there instantly. It takes a bit longer than a 5. If I try it for 37 here, you already see now we have a significant gap here, a significant pause before this appears. So this takes longer and longer for very small increases here. And this, I can tell you, is not quadratic time. For quadratic time, you would have no problem with such a small number. This indeed is exponential time complexity, because we do not just add 1 function call with every increase in n, but we add whole new branches in this recursive tree. And every branch consists of other branches, and therefore this quickly grows to a number that your computer won't be able to handle. And therefore this, of course, is a horrible solution for a problem we already solved with linear time complexity. This is an example for a recursive function that's not better than the loop-based solution. This takes far longer. It's far slower. It's not a good solution for this problem. It might look elegant, but it is a horrible solution like that. Now, there is a way of improving this, though. Now, in the last lecture, we had a look at this Fibonacci solution with our recursive calls, and you learned that it's bad because it's actually O of 2 at the power of n. Now, how do I know that it's this kind of exponential growth and that it's not a quadratic or a cubic function? Well, we can implement a simple check here that allows us to find out. Let's add a counter variable, which is 0 initially, and then here I add 1 to it in every call of the fib function. So that will also increase the counter if we have those nested calls. Now I will comment this out here and instead now call fib with, let's say, 5, and thereafter console log the counter. I don't care about the result of this call for 5, so I'll just log the counter and then reset the counter thereafter. And then I'll repeat this and also call it for 10, and also call it for 20, and also call it for 30 here. And now let's see what we get here. You see I get 15, 170, and then some big numbers. Now that's interesting. Now that's the output for 5, 10, 20, and 30. That's our n. Now if we had quadratic time, then for n equal to 5, we would expect 5 times 5, because that's 5 squared. Now this gives us 25, but that doesn't say much. It's a bigger number than we actually got, so it seems that it's less than quadratic time. But for small n's, we can have deviations. So let's check a bigger n. Let's check 10. For 10, if it were n squared, we have 10 times 10, which is 100, but we see, oh, we had 177 executions. So now we already see, for a tiny increase in n, we certainly don't have quadratic time. Because if we had quadratic time, we shouldn't see an increase in operations from 15 to 177. Instead, we should see 4 times as many operations, right? Because for a quadratic time, we go from 25 to 100. So if we went from 15 to 60 here, it would maybe be quadratic time, but that's not what we have here. So we can rule out quadratic time with this simple check. Now, what about cubic time? Maybe we have cubic time. That would mean that for 5, we have 5 times 5 times 5. 125. And for 10, we have 10 times 10 times 10. 1000. Now that's bigger than what we have here. So maybe we have cubic time. We should validate it for a bigger n though, because we have quite a gap between 177 and 1000. So maybe we're between quadratic and cubic time. Let's validate for 20. If we had cubic time for 20, we would get 20 times 20 times 20, 8000. And what do we have? Oh, we have 22,000. So you're seeing the pattern here. For relatively small increases in n, our number of operations grows quickly, way quicker than it would for cubic or quadratic time. And we can continue to play this game, even if I take 20, so n at the power of 4. Even in that case, here we have 160,000. Yes, that's bigger. But if we have a look at slightly bigger n's, like 30, we see that 30 times 30 times 30 times 30 is 810,000. But here we already have over 2 million, right? So this will lead nowhere. It's definitely not n at the power of anything. Instead, only 2 at the power of n yields results that explain such big jumps. Because indeed, 2 at the power of n, if I have math pow, 2 at the power of 30, for example, yields this number. Now this is certainly bigger than the number we got there. So in reality, for this algorithm, we might be a bit better than 2 at the power of n. But since we're always just caring about the general trend, we're definitely closer to this, especially if we test this for bigger and bigger n's. than we are to cubic, quadratic, or any of those time complexities. And that's how you can validate this. Now, with experience, you simply see something like this. You don't need to run these calculations I just ran, but to explain it to you that I don't make up this value, but that there is a reason behind assuming this time complexity, I think that's a nice way of understanding why cubic and quadratic time and all those time complexities are not suited to explain this strong growth which we indeed have here. So we had a look at this recursive Fibonacci function, and we found out that it provides us with a solution that isn't really that great. By calling itself twice per iteration, we ended up with an exponential time complexity, and that is way worse than the loop-based solution we had at a look earlier, which gave us linear time complexity. So does this mean that we're at the end with recursive solutions for this problem? This wouldn't be too horrible or too bad. I mean, we do have a loop-based solution, and recursion might be better for other problems. But in order to understand more complex problems we're going to dive in later, we now have to understand how we still could make recursion work with this problem as well. We can use a technique for that, which is called dynamic programming. So what is dynamic programming? How does this help us with this problem or with this exponential time complexity? Well, we had a look at recursion. Now we're going to combine this with a technique called memoization, which essentially means that we're going to store some data. It's not memorization, but memoization. That's a technical term for basically keeping some data around for the execution of a function for a certain process, in this case, for this recursion. So we're going to combine recursion with some data that's going to be stored. Recursion, of course, is great for repeated computations, but as we saw, it can lead to duplicate work depending on your problem you're solving, depending on your function. Remember that with recursion, in this case, with the Fibonacci function, we had those branches here, which in the end are the same computations executed multiple times. So we're repeating certain steps here. We're repeating the same calculation multiple times, and that's exactly what's causing this exponential growth rate. That's what's causing the problem. So how does data storage or storing some data help us? Well, we can avoid unnecessary recursive steps if we store certain data for this process, for this recursion. To be precise, we could store intermediate results and make sure that they're available to every new function execution. Then we could check if we already made a certain calculation. Going back to this picture, we could check if we already have a result for fib2, and then we don't need to do this fib2 calculation a second time. We can save that extra function call, which in turn saves us the extra function calls for fib1 and fib0. That's the idea. If we can eliminate extra function calls, we eliminate whole branches of this recursive tree. And that's what dynamic programming is all about. It's about recursion, solving a certain problem, with memoization. So with storing some intermediate results, with storing some data to optimize this recursion process. So therefore, back at our recursive Fibonacci function, let's see how we could improve that with memoization, so by adding such a storage. Well, in the end, we want some global storage, which is available in every function execution, where we can store the results we derive. So of course, for the first function execution, that storage will be empty, but the more functions we execute, the more results we derive for different numbers, for different positions we retrieve from that Fibonacci sequence, the more our storage will be populated with those intermediate results. That's the idea. So therefore, we could set up a global storage, let's say a global object, which we could name memo, and we could dynamically add key value pairs to that object with every iteration. This might work, but the problem with that is that we have one object, and if we call fib multiple times, let's say for different numbers, we're reusing one and the same object. This can actually be great because on the second call, we already take advantage of all the intermediate results we derived in the first call. But if you had a function where the input produces totally different values, then having such a globally stored object could be very bad because you might be getting incorrect results in your next function execution. Hence, we're not going to write it like this. Instead, the idea is that every recursive process, every Fibonacci number we try to retrieve gets its own storage, which is only used for this recursive tree. So that fib5 and fib6 here would generate different storages or would use different storages. And for that, all we need to do is we need to provide a second argument here to fib, let's say memo or just mem or whatever you want to call it. I'll name it memo. And that will be our storage. Now we can call fib5 by passing an empty object as a second argument, and we do the same here for fib6. Initially it's empty because this storage should get populated whilst this recursive process is running, because we want to store intermediate results. Now the idea is that inside of our function, inside of the fib function, we introduce a result helper variable, which initially is empty. And then here in this if check, we set result equal to 1. Otherwise, down there, we set result equal to this. Now we'll put this into an else branch, because now after the if-else statement, we can return result. So thus far, that's just a rewritten version of what we had before using a helper variable. Now, why do I use this helper variable? Because now the idea is that we don't just return result for every function call, and that includes the nested function calls, of course, but that we also store it in our intermediate storage here. So we can access memo, and since this is a JavaScript object, we can dynamically add properties. With the square bracket notation, we can use a variable which holds the name we want to use for the key we're going to add. And that could be n, so that we have something like 1 as a property name, or 2, or 3, or 4, and the value for that key name should be the Fibonacci number that was derived. So we set this equal to result. So the idea is when we execute fib, we execute those nested functions, and ultimately those functions are going to return values. And before we then go further up in our recursion tree, we already store those returned intermediate values, and we're always working on one and the same object. Now, to make sure those nested recursion calls also have that same object available, we simply pass it as a second argument here. So now that's not an empty object, but that one object which we initially got here. And since objects are reference types in JavaScript, we're always acting on the same object. So when we dynamically add a property to that object, that property is going to be available in other fib function calls of that overall main function call here. Now fib5 and fib6, these two lines down there, have their own independent storages, the objects we're feeding in here. But all nested calls then operate on the same storage object. And that storage object also receives our result. Now, thus far we're storing intermediate results, but we're not doing anything with it. So currently we have no optimization in place. Therefore, one last step is missing. Here in our fib function, we now initially want to check if for the n we're running this function, we already have an entry in our memo object. Now, at first this will not be the case, but once we had a couple of nested function calls, we might have already derived a value for fib2 or fib1 or fib3 or whatever is happening down there. So we check if memo n is a thing. If such a key does not exist yet, this returns undefined, which is falsy. So we won't make it in there. But if this returns anything but that, we actually will make it in there, and we can now simply return memo n, so that stored intermediate result. And the rest of the code is therefore then skipped. And as a result, for some of our nested function calls, we won't have to do more nested calls. Instead, we find such a stored value and we can skip all other steps. So that means that our solution, which previously led to this tree of function calls, now with our new solution is optimized because we get rid of a whole branch of that tree. And hence we have way less function executions. And of course, for bigger numbers, for bigger n's, that effect is even more visible. So let's take a look at that. And to see whether we really improved, I'll again add a counter variable here. And I'll increment that counter here at the very beginning of the fib function. And that allows us to utilize that counter to see how many iterations we had. So here I will then console log counter and then also reset counter so that we can do the same here after calling it for fib6. And now we can even do that for way bigger numbers, let's say for 20 and also for 50, which are numbers I didn't even check before. Now you will see this works. So if we now save this, and we go to the browser, and I reload there, you see that's super fast. And these are not our Fibonacci numbers. Instead, these are our iterations. And you see for n equal to 50, I have 99 as a value there. Now, just to quickly compare this, if we have a look at our previous implementation here, if I bring back this approach real quick, we didn't even try this for 50. We tried it for 30. Now, it might be nice to see what the difference is for that. So let's quickly bring back that old approach here, fib recursive JS, and reload with that. And we see for 30, that's over 2 million, close to 3 million function calls. So pretty much. Now I will actually swap this back here to app.js and go back to app.js. And here for 30, if I change that, here for 30, so the last number which is now going to get output is just 59. I would say that's a bit less than almost 3 million. So the question there for now is, what's our new time complexity with that? It's certainly not exponential time complexity anymore. What is it instead? And the answer is, it's linear time complexity. In the end, you can see it pretty well here. For fib20, so for an n of 20, we had 39 iterations. For 30, we have 59. So for an increase in n of 10, we add 20 iterations. So 2n sounds like our time complexity, and as you learned, we then simplify this to just O of n because we care about the general trend. So we went from O of 2 at the power of n, which is exponential time complexity, to just O of n, which is a huge improvement. And the reason for that is what I just showed on the slide before. We're skipping entire branches of our tree with this optimization technique, with the help of dynamic programming. Now, dynamic programming is pretty powerful, as you saw. With this memoization technique with our storage, we build up a storage that looks something like this in the end. For different n's, we store different values, and that makes going through our recursive calls much easier and skips unnecessary branches. We can also look into our storage here, by the way. I have my nice counter here, but if you want to see how the storage looks like, we could add a new constant, memo here, which is this empty object, and feed this here into our fib5 call. Not in the other calls, just in this call. And then, besides outputting the counter here, we can also output this memo object so that we see how that looks like after executing our Fibonacci function here. Initially, it's an empty object. Now let's see what it's like after this finished executing. For that, if I now reload, you see that's my object. And that's what I meant on the slide. We have 1, 1 stored as values for the different indexes by which we want to retrieve those values. And then, since we're retrieving fib5 here, the highest stored value is 5 because that was the last value we retrieved and stored before we finished. And there we stored 8 as a value in the Fibonacci sequence. So in the end here, we have all these key value pairs. We have the different positions in the sequence and the Fibonacci numbers for those positions. And the highest number we have and the highest position is just the position we fetched, because that's the last position we add here before we overall return in that main function call. And that's what I meant here on the slide. Over time, we build up such a storage with all those values stored. So overall, we of course, in this case, store the Fibonacci sequence in this storage. Now, since that is the case, of course, what we're doing essentially with this recursive approach is not that different from what we saw earlier with the loop-based solution. We're following a bottom-up approach in the end. We're building up all the data we need up to the n we need, and then we get that value for that n and finish the function execution. And that's called the bottom-up approach, and we already did that before, right? When we had the Fibonacci function without recursion, where we just built up this array here, and that's what we implemented in the last course section already. This already was following this bottom-up approach, because for the bottom-up approach, we don't need recursion. All we need in this case is a loop where we build up an array, and once the array is long enough, once we can retrieve the nth element, we do so and we cancel, we finish the function execution. Now, this bottom-up approach sometimes is an alternative to the recursive solution. And in case of the Fibonacci sequence, we can either use that bottom-up approach with the loop, which we saw earlier, or the dynamic programming approach with recursion, which we now implemented. You can do both because they also have the same time complexity, which is O of n, right? That's the same now for this dynamic programming approach as well as for the bottom-up approach with the loop. You can use both here. Now, throughout this module, we'll also see other problems where recursion simply gives us a more elegant solution, or sometimes recursion is also the only solution. In the case of the Fibonacci sequence, that's not the case, but it's simply a great example for introducing recursion and problems that might be connected to recursion, which is why I chose to dive deeper into that specific problem, into that specific algorithm. I want to make it clear, though, that this is now not better or worse than the loop-based solution. You can use either of the two solutions. The only solution that you might want to avoid is the recursive solution without our memoization, without the storage, because that, as you saw, had a pretty bad time complexity. And now with that out of the way, we got a lot of tools at our hand to solve algorithms. Now, we also saw some algorithms already, but they were all about math problems, about mathematical questions. Now, in the next section, we're going to dive into search algorithms, which help us find elements in lists. We had a look at a lot of important basics when it comes to deriving algorithms in JavaScript and when it comes to judging them. Thus far, we primarily had a look at math problems, though. We had a lot of algorithms that dealt with certain mathematical issues or derived certain mathematical results. In this section, we're going to dive into a different category of algorithms. We're going to dive into search algorithms. So, programs, algorithms that help us find things in arrays. That's what this module is all about. Now, first of all, we'll have a brief look at why we have search algorithms, or why there might be more than one way of finding something. But then we'll most importantly have a look at two core, very important search algorithms you should know as a developer. And that's, by the way, a difference to the math algorithms we had a look at thus far. Maybe with the exception of the factorial, which is really easy to memorize. You don't need to know all these math problems necessarily. Finding elements in an array is a common task, though, and therefore the algorithms we're going to have a look at in this module are algorithms I recommend that you keep in mind. Now, the algorithms I'm talking about are the linear search algorithm, which is a relatively trivial search algorithm, and the binary search algorithm. And in conjunction with that and its recursive implementation, which we'll also have a look at, we will also dive into a core concept which is called the master theorem. in this module. The master theorem allows us to judge the performance of a recursive algorithm if we can't just count execution steps, but we'll have a look at that in detail once the time is ripe. Now that's this module. Let's not waste any time and dive right in. So, what are search algorithms and why might we need them? It's quite common in programming that you're confronted with lists of data, with an array of data. That can be an array of numbers, like it is on this slide, but it can of course be an array with any kind of data. Doesn't have to be numbers. It can be strings, it can be objects, anything like that. But I'll focus on number arrays here because that's easiest and makes understanding these algorithms easier as well. Generally, you can work with any arrays though. Now, in such an array of data, you might be looking for a certain element. Let's say we're looking for the number 5. And then you need an algorithm, you need some logic that in the end makes sure that if you're looking for a certain element, that element is found and retrieved from the array, or you're getting an error message or some dummy return value if the element is not found. Now you can actually use different algorithms for different kinds of lists, and these different algorithms also have different time complexities. And there are two essential algorithms, and these are the algorithms we're going to have a look at in this module. Let's start with the linear search algorithm. It's the easiest search algorithm, which does not mean that it's a bad algorithm. Let's consider an array of data that looks like that. And again, it wouldn't have to be numbers, but that's easiest and therefore makes understanding this algorithm easier. Now let's say we're looking for the number 5. The linear search algorithm is a very simple algorithm. The linear search algorithm does what you probably would do as well if you're confronted with the task of finding the element with the value 5 in this array. You would probably have a look at every element in the array, and the first time you see 5, you stop and you return that value and or the index of that value. And that's exactly what the linear search algorithm does. It goes through this array, through this list of data, step by step, from the beginning to the end, and it stops once it finds the value it's looking for. And then it returns that value or the index of that value, whatever you want to have. So linear search is really simple, and it works on ordered and unordered lists. So the list doesn't have to be sorted because you're simply having a look at all items until you find the element for the first time anyways. And that's important. If you have the same element twice in that list in this array, you would simply stop the first time you find it. That's the idea behind such search algorithms. You return the first found element. Now that's linear search. Let's write such an algorithm and let's thereafter judge the time complexity. Now for that, I'm back in my dummy project, no HTML content, just an empty app.js file, and in there we can now write our linear search algorithm. For that, I'll add a new function here, linear search, or just find element, whatever you want to name it, but we'll use the linear search algorithm here. And what we get here as an argument should be the array of data in which we want to find the element, and then of course the element we're looking for, element or seek element or element you're looking for. I'll just name it element here. So these are the two values which we need here for this algorithm to work, or for this function to do its job. And then the idea simply is that we have some array of numbers, let's say, and as I mentioned on the slide, this doesn't have to be ordered. You can have any order here. No sorted array is needed. And then we can call find element here, like this, pass in the array, pass in the element we're looking for, and be done with it. Whoops, of course, without function. So that when we console log this, we would then return the index of the element where it is at. Because the value itself makes no sense. We know that we're looking for 10. So we want to rather return the position of that value. This is how I want to call it. Now, how would we implement this? As I mentioned on the slide, the linear search algorithm is really trivial. You simply visit every element in the array and check if that's the value you're looking for. Now, if you are working on an array of numbers, you simply compare the values. The same would be true for an array of strings. If you had an array of objects, then of course a comparison with the equal operator would not work, but I'll come back to that in a later step. For now, let's focus on numbers and string arrays. So how could this algorithm work, therefore? Well, in the end, we can write a for loop there, a regular for loop with an iterating variable, or a for-off loop. And I'll go for the for-off loop here and have a look at every item in my array, so with for item of array. And then I will simply have a look at this item, because this goes through the entire array, and I compare this item to the element I'm looking for. So in the end, I just check if item is equal to element, and if that is equal, I know that I found the right item. But now I'm interested in the index, right? So since I have a for-off loop here, I would have to manually keep track of that with index 0 at the beginning, and then after every iteration, or at the end of every iteration, I increment index, and therefore here I can then return index. And this would be one possible implementation. Of course, you don't need that index helper variable if you use a for loop with your own iterating variable, or if you use array for each, right? With that for each method, you also can pass in a function that automatically gets the item and the index as an argument. You can use whatever approach you want. So this is my algorithm here, and this should already do the trick. If everything works, I should be able to run this code, and for the element 10, we should now get 2 as a result, because the index of 10 is 2. 0, 1, 2. Let's have a look, save this, reload, and I get 2. Now let's maybe also verify this with a different number. Let's say 33, which is at index 4. 0, 1, 2, 3, 4. So we should now see 2 and 4 in the console, and we do. And that's already all. That's the linear search algorithm. Now, if we had an array of strings, it would work in exactly the same way, because strings, like numbers, are primitive values. But for an array of objects, this would not work. If I simply add my other array down there, objects, and in there I have an object with a name Max and an age of 31, and here I have name Manu and an age of 32, let's say. I have this array with these two elements. Here, if I then want to find an element in this objects array, let's say I want to find Manu, which is who is at index 1, you would see that this does not work. Instead, I get undefined as a result, because I don't find this value at all. Now, why is that happening? Because objects are reference values in JavaScript. That means that this object down there in line 21 is a totally different object than the one in line 18. They look similar to us humans, but as you should know, these are two different objects in two different places in memory, and when we compare them with the equal operator, no matter if it's the one with the double or the triple equal sign, we check for value equality, and those don't have the same values. These are different places in memory, they have different addresses, so if we compare them, no matter if we use 2 or 3 equal signs, this will never yield true. So how could we find it with our algorithm then? Well, if we would use the same reference, so if I had my person constant here, and I stored this object there, and I then add person in objects, and I look for exactly that person down there. Now, since it's only defined once, and then stored in the constant, we are dealing with the exact same object in memory. Now, our algorithm would work, as you can tell, but that's maybe not what you want. Instead, if you're writing a linear search algorithm that deals with objects, you might want to fine-tune your comparison logic. If you're dealing with an object in there, you might want to tweak this algorithm and check if the type of element is equal to object, so that you first of all verify whether you're dealing with an object with a reference value or not. And if element is unequal to null, because null would also be considered an object, but you don't want to compare null the way we're going to compare objects. You can compare null with this comparison. So if we have an object, but it's not null, null would be treated as an object, then we want to run our object-specific comparison logic. Now, if you know that this algorithm, this function, is only going to run on specific types of objects with a certain structure, you could hard code that comparison in here. So we could say, now that we know that it's an object and that it's not null, we know we're always getting objects which have a name and an age key. And I'll, by the way, revert this down there. So we always have object with a name and an age key. If we know this with certainty, we could say, we know we always want to compare by name, let's say, because we know that's our main condition, our main criteria. Well, then we can check if element name is equal to item.name. And if that's the case, we can return the index. So now we have a very specific comparison, which really only works on objects that have a name field and which really only makes sense if we know that we want to decide by name. So if maybe the age is different, but the name is equal, we would still find that element with the logic we defined up there. Of course, we could add an extra condition and say, and the age also should be equal. And now we would really only return that index if the age is equal. So let me fix that. But again, we have a very specific comparison logic now. Nonetheless, if I now reload this, we find the element at index 1. And just to prove that the age has an effect, if I do change this to 33 down there, but not here, we get undefined. So we really check for both. But still, again, this is a very specific algorithm that really only works with objects that have a name and an age key. Might be what you need, but might also not be what you need. You could make it more flexible by expecting a third parameter, comparator fn, comparator function, you could say, which is a function you expect to get as a parameter which you call from inside this function, from inside this algorithm. And that would be a function that returns true or false, so that the one who's calling find element passes you the comparison function, and your find element function doesn't have to know in advance which kind of data you're getting. So here in this if check, we could then just call comparator function and pass in, let's say, the element and the item. And now comparator function should be a function that returns true or false for these two given inputs. And now it would be our task down there, where we call find element, that we pass in a function, and that can be an anonymous function, that gets our element and our item, and that then returns true or false. And now here we know specifically which kind of data we're feeding in for this specific function call. So now here we can simply return element name equals it, item name, if we cared about the name only. And now we would find that element here by name, because that's the logic we defined for this specific find element call. So if I reload, I get 1 again. And that's just a little addition I wanted to show here. The general idea of the linear search algorithm does not change just by adding an extra if check. This is just how you could make it more flexible to also work with objects. The key takeaway for this algorithm is that you simply have a loop and have a look at every element. And the way you then compare the element to the element you got as an input, well, that is something you can implement in a dynamic way with such a comparator function, or if you know you're only dealing with primitive values, in this more simple baked-in way. That was just an addition. Key takeaway is that you have a loop where you visit every element until you find an equal element. If you don't find any element at all, in this case, we return undefined. Now that we had a look at the linear search algorithm, the question of course is, what is its time complexity? Since we have a loop that goes through all elements in an array, we can have a look at a couple of different cases, to be precise at the good old best case, average case, and worst case. Why? Because for such an algorithm, where we look for a specific value, we can imagine a best case where the item we're searching is the very first item in the list. Right? Here we have find element, and if we take that number example, if I'm looking for the number 5 here, that's the first element. So this entire loop will only run once, because the very first element already is the element for which we will return true here. Hence, in this best case scenario, we actually have a constant time complexity because we only have one iteration. And if we know with certainty that the item we're looking for is always the first item, we always have this constant time complexity. But of course, we also have the worst case. The item we're looking for is the very last item in the list. In this example here, with the numbers again, that would be 51. It's the last item, and that means that if we're looking for this item, this loop has to run through the entire array, and only the very last item we're looking at is the item that's equal to our element. Therefore, in this worst case, we have a time complexity of O of n, linear time complexity, because the bigger our n is, the more iterations we need, but we have a linear relationship. It's not growing exponentially or anything like that because we only have one loop iteration per n, so to say. Now, what's our average case then? The average case is the case we typically have, and that of course is that we don't know where the item is at. Because if you think about it, if we would know in advance where the item is, we wouldn't need to search for it, right? So typically we have a random order or a random position of the item, I should say, so we don't know where the item is. And then this tends to be O of n. Now, of course, we might still end up with the best case. Maybe the item is the first item, but we don't know in advance, and therefore we simplify this to O of n. We assume the worst case, and we're probably better off than that in the majority of cases. But since we don't know, we have a tendency towards O of n because that's the general runtime of this algorithm. In this example again, if we're looking for 5, we're done after one iteration. 51, we need all iterations. 10, we need 3 iterations, and so on. That's why we have this average case. So overall, time complexity here is pretty straightforward, and the linear search algorithm in general is pretty straightforward. Now, of course, for arrays, you already have a function that does such a search, by the way. And that would be your find method. That's already baked into JavaScript, and it takes a function that should return true if it's the element you're looking for. And you also have find index if you're interested in the index. Then here you get the element for which this function is called, because this runs on all elements in the array. And you have to return true if this is the element you're looking for, or 5 otherwise. So in the end, we just re-implemented that in a bit of a more dynamic way, or however you want to call it. But in the end, this built-in find and find index method is already a function that does what we want to do in such a linear way. Nonetheless, it helps a lot to understand this, and if you want to fine-tune what happens during that search process, like here, where we build a function that works with objects and primitive values, then building such a custom function can be worth it. Now, visiting every single element is maybe not the best possible approach. We'll see if we can do better, but it's also not horrible. Linear time complexity is something you might want to try to improve if you can, but often you can also live with it. Nonetheless, we're now going to have a look at another algorithm that does actually better than linear time complexity. We learned about linear search. Now it's time for binary search. Binary search is an algorithm that actually will give us a result better than linear time complexity, and it also solves the problem of finding a certain element in a list of elements. However, there's one important restriction with binary search. Linear search worked on ordered and unordered lists. So the lists didn't have to be sorted. The items in the array could be in any order. Binary search, on the other hand, only works on ordered lists. It does not work on unordered lists. So you need to sort your list first. And of course, you need to take that into account. If you have an unordered list, and you need to sort that first, even the fact that binary search, as you will learn, performs better than linear search, doesn't help that much because that sorting of the list also takes up some performance. We'll dive into sort algorithms in the next section, by the way. For now, let's focus on search. So for binary search to work, you need a sorted list. You need a list where all the items are sorted in some order, ascending or descending, up to you, typically ascending. Now for this module, we'll assume we just have such lists. In the next module, we will learn how we can sort arrays with different algorithms. Now, if you have a sorted array, what you do with binary search is in the end you find the median, you find the element in the middle. Now, if you have an array with, let's say, 6 items instead of 7 as we have here, then you take one item below the theoretical middle. So you take the item closest to the middle of the list, and then what you do is you check if that's the item you're looking for. So here I'm looking for 5. 10 is in the middle. That's not the item I'm looking for, but that's what we do first. We check if it is the item we're looking for. Now, if it's not the element we're looking for, we take the half of the list in which the item must be. Since it's sorted, we can find out if the item we're looking for is smaller or bigger than the item we just checked. So 10 is bigger. Since the list is sorted, we know that the item we're looking for, the 5, has to be in the first half of the list. So we then take this as a new list, and on that list, we repeat the process. We again have a look at the middle, check if it's the item we're looking for, and if not, check in which half the item has to be, and so on. That's binary search. And because we're splitting this in half every time, we will actually be able to do better than linear time complexity, as you will learn. Now let's implement this algorithm. For that, I'm back in an empty app.js file again, and I will add my find element function here again. And again, the idea is that we have an array now of ordered elements. So where, well, they're typically ordered in ascending order, like it's here. And then, let me actually add one extra element. And then we are able to call find element, pass in the array, pass in the item we're looking for. Let's say that's 99. And again, I want to get the index of that element here. Of course, you can return whatever you want, but here, let's say I'm interested in the index. Now we have to build this function. We have to build this algorithm. So in this function, I expect to get 2 parameters again, and that would be my sorted array and my element I'm looking for. Of course, you don't have to name this sorted array. I just want to make it clear that for this algorithm, you need a sorted array. You could also expect a comparator function if you again want to write a flexible function that also works with objects and so on. I will leave it out here because that part would be exactly equal to the linear search algorithm. So if you want to implement it, you can just take the same logic from there. Here, I'll just focus on the algorithm itself and therefore just implement it here with primitive values. So we got these 2 parameters. What are we doing now? Well, now we first of all need to find the middle element. Now here you see I actually have 6 elements. So the middle would actually normally be at 3.5, right? That's right in the middle. So actually between the 9 and the 13. And that of course doesn't make sense. So what we'll do instead is we'll take the 9 as the middle. Now to derive this mathematically, we have a look at our start index, which is 0, of course, because I want to start at the beginning, and at the end index. And that is our sorted array length minus 1. Because the index starts at 0, that's why length minus 1. Now, with that, we can derive a middle index. And by the way, these should be variables with let, because we're going to change those. We're not going to change that middle index here. So I have a middle index here, and that will actually be my end index minus my start index divided by 2. That's how we mathematically derive the element, well, between these 2 numbers. But since this would be 3.5 for this array, we actually use the built-in math floor method to round this down to the closest integer. So 3.5 would become 3 with that function here. That's our middle index. And now we check if the element we're looking at, if that is actually equal to sorted array middle index. So the element in the sorted array at the middle index. And if it is equal, we return the middle index, because that's the index of the element we're looking for, right? The element with the middle index is equal, so the element we're looking for has that middle index. That's what we're returning. If I save this, and I run that, I of course get undefined because 99 is not here in the middle. If I would look for 9, on the other hand, I would get 2 because 9 turns out to be our middle item calculated by that logic. So that would work, but of course that's not a good algorithm. It finds exactly one element. So I revert this to 99, and now we need a loop. We need to do that splitting of the list, which I mentioned on the slide, because this currently only works for one element. So let's derive a new middle index every time we fail to find the element. So we can add a while loop, because I want to keep on going as long as a condition is met, and that condition is that my start index is smaller or equal than my end index, because I'm going to change these indexes every time we now split the list. Now that logic goes into the while loop, so that we repeat that logic. But right now, of course, we have an infinite loop. So if we find the element, we're still going to make that comparison. If we find the element, we're done. But if we don't find it, so after this if check, if we don't make it in the if check, we know we didn't find the element. And then we need to do something else. And here we now need to split our list, but of course for that we need to know at which half of the list we should have a look at. Since it's ordered, we know that if the middle element isn't the element we're looking for, there's only one sub-list that makes sense to dive in further. Because here I'm looking for 99, 9 was not the element I was looking for. It makes no sense to search in the first half of the list therefore, because that's smaller than 9 anyways. We know that 99 is bigger than 9, so we have to look in the other half of the list, in the bigger than 9 half of the list. So in this half here. And therefore what we do if we didn't find the element is we check if our sorted array middle index, so the element we're looking at, if that is actually smaller than the element we're looking for. So in this case, the element we're looking for is 99. The element at the middle index would be 9. So 9 would be smaller than 99. In this specific scenario, we would make it in there. Now, if we make it in there, we know we have to look at the second half of the list. So what we simply do here is we change our start index to our middle index plus 1. Now the loop runs again and we derive a new middle index, which takes our new updated start index into account. The end index does not change. So actually we could turn this into a constant here, but it will soon change. So let's keep it a let. For this approach here, or for this scenario, it does not change though. The start index does change. So for the next iteration, start index is the old middle index plus 1. Middle index was 2 here for the first iteration, because the index of the value 9 is 2. So for the next iteration, our new start index is 3, 13. And that's exactly the element we want to start at. So this is the next list we're looking at because of this simple change. Now, of course, the item in the middle could also be bigger than the element we're looking for though. It's not the case here for 99, but if I would be looking for 1 instead, we would have the case that the element at the middle index, 9, was bigger than the element we're looking for. I'll revert to 99, but we could have that other case too. So we also want to have an else statement here. Since I'm checking for smaller than here, we automatically look for bigger than here. We don't need to check for equality because we're already doing that there in this first if check. So if the element in the middle is now bigger than the element we're looking for, we change the end index. We change the end index to be the middle index minus 1. We leave the start index untouched. Why? Because the start index initially is 0. If the element we're looking for is smaller than the element in the middle, we want to dive into that first half of the list, and that half of course starts with 0. So the only thing that needs to change is the end index, because we don't want to go through the entire list anymore. We just want to go up to the middle index minus 1, because we know it's not the item in the middle. So this will be our new list we then have a look at. And that's why we change start and end index depending on whether the element we're looking for is smaller or bigger than the element in the middle. And that is all. With that, we have a while loop that will gradually split this list. It will split the list with every iteration into 2 pieces, into 2 halves, until we finally have the element we're looking for in the middle or as the last remaining item. In this concrete example here, the first element we have in the middle is 9, as I explained, because That's in the middle, since we don't have a perfect middle here. That's why we use math floor. So 9 is our first middle element. We then see that 99 is not equal to it, so we don't make it in there. Instead, we check these conditions. And of course, 9 is smaller than the element we're looking for, which is 99 in this case. So this condition here kicks in, this first part. The element in the middle, 9, is smaller than the 99. So we change the start index. So the next time the while loop runs, we have a new middle index, which is our old end index, which is still the last index of this list. So that would be 0, 1, 2, 3, 4, 5. So 5 is still our end index, but we deduct our new start index from that, which is the index of the element 13, which is 3. So we have 5 minus 3, divide this by 2, and we end up with a value of 1 therefore. So we would now check the element with index 1 here, and that doesn't make sense, right? Well, we're not entirely done yet. This logic here is not entirely correct. We need to actually add something to that number derived here, and that's our start index. For the first iteration, this does not matter because start index is 0 anyways. But if we change the start index at any point, it does matter because we need to, well, add the old start index to the new derived middle index here, so that we correctly shift the middle index and we only focus on the half that's of interest to us. And with this adjustment made up there, we can have a look at that again. 99 is the element we're looking for, 9 is the first middle, which is not met. So we have a look at the second half because of this check, because now the new start index is the old middle index, 2 plus 1, so 3, so of the element 13. 3 is the new start index. The end index is still 5, so we have 5 minus 3 here, which is 2, divided by 2 is 1. But we now add the start index to that, and the new start index was 3. So it's 3 plus 1, it's 4, and that's correct. So the new middle index we're now looking at has an index of 4, which is 99. And in this case, in this example, that will already be the element we're looking for. So if I now save this and I reload, I get 4 as an index returned. That's how this binary search algorithm works. And in case you're wondering how often this loop runs, well, let's log running here. If I do that and I reload, you see in this case it runs twice. These 2 iterations I just explained verbally a second ago. So that's this algorithm. That's the binary search algorithm. And since we split the list with every iteration, it's of course better than the linear search because we don't have to visit every element. On the other hand, we need a sorted array here. And therefore, if you have an unsorted array, you need to sort it first, which of course also takes an algorithm on its own and which also takes up performance. But again, sorting is the subject of the next module. So what's the time complexity of binary search then? Again, we have our different cases, and the best case is that the item we're looking for is right in the middle. Not in the start, but in the middle, because the middle is where we first have a look at. In our example here, that would be the case if I'm looking for 9. If I'm looking for 9, that's the first element we're checking, as you learned. And therefore, if I again log this real quick here, you will see that we only see running once, because immediately we find the element. So that's the best case. The element we're looking for is right in the middle of our array. In this case, we have O of 1, constant time, because we only need 1 iteration. But again, just as with the linear search, we of course don't know this in advance. We also might have the worst case, where the item we're looking for is exactly at the beginning or the end. Since we split the list in half every time, we're always having a look at the middle first. So we only reach the end or the beginning of the list at the very end of all our iterations. And in this case, of course, we don't have constant time complexity. But which time complexity do we have? O of n? Actually not. Actually, we would have logarithmic time, because we split our problem set, our array, in half with every iteration. So no matter how big our n is, no matter how long our array is, we're never going to go through all array items. That's why we don't have linear time complexity. We're splitting the array in half every time, and that gives us logarithmic time complexity. You might remember this power of algorithm we had in the math section. There we also had logarithmic time, because what we did there is also that we divided the number by 2 in every iteration. So we never would run through all the numbers up to that number. We always split it in 2, and that means we have a much smaller problem set, and with every iteration we split it in 2. Not just once, which would then be n divided by 2 as a time complexity or something like that, but with every iteration. So with every iteration it gets smaller and smaller. And it's the same here. Since we have a new middle index for every iteration and we start at that middle index in the end, we split our array into 2 with every iteration and derive a new array. That's why we have O of log n here as the time complexity. The average case is that we have a sorted list, but we don't know where the item is, and that will be our default case. And just as before with the linear search, this here also therefore tends to be our worst case. We might be better than that, but we don't know. So in the end, we assume we have the worst case, we could say. So often will be a bit better, sometimes will be exactly at the worst case, rarely will be in the best case. Therefore, our time complexity here would also be O log n. That are the time complexities here. And that's a general good rule of thumb. If you're splitting the problem set into 2 or even smaller, divided by 3 or 4, with every iteration, you're dealing with logarithmic time. Now we implemented binary search, and we did so with this loop-based solution. Now this is a perfectly fine solution, and you can leave it the way it is. Nonetheless, I also want to show you a recursive solution which we can use instead, and I will then show you how you can derive the time complexity of that solution. So let's again add our findElement function here, where we get our sorted array and the element we're looking for. And in there, I basically again want to write the same binary search algorithm, but now utilizing recursion instead of a loop. The goal, of course, is the same as before. Therefore, if I have this array and I want to retrieve the item 9 or the index of that item, then I want to get the same result as before. Actually, let's start with 99. So here's findElement. How do we write this in a recursive way? Well, we can actually copy that logic from before over into this function here. But now, of course, we'll tweak that loop part. We'll actually get rid of that loop here and replace it with something else. So I still have my start index, the end index, the middle index, which is derived as before, the comparison here, which, since we'll add recursion soon, will be my base case. So this if check here is the base case, which will get us out of the recursion, because here we're not calling findElement, we are returning a value here. And now down there, we have to, well, work on the recursion. So how do we do that? If the element we're looking for is greater than the element we currently are looking at in our sorted array, I now want to return a call to findElement itself. So that's a recursive step. I call findElement itself. And what I pass in is my sorted array, but of course now just a part of that array. To be precise, the part, the half of the array in which this element must be. So I take my sorted array, and we can use the slice method on the array to create a new array, which is a slice of the old array. So which is a part of the old array, not the entire array. Slice takes 2 arguments for that, the start and the end index. And here we simply would take our new start index and our existing end index. This, by the way, means that now I'm shrinking the array. Hence, when we derive the middle index here, we no longer have to add start index to the number here. We can just get our middle index like this, because now that's the difference to the loop solution from before. Now we get a new array every time findElement runs, and that new array is already smaller every time we call it. So therefore, we always can get the middle of that array, because the array we get already is the entire array in which we want to look. So previously, we basically worked with the indexes to narrow down the array. Now we're narrowing down the array itself. So I pass the slice of my array to that function call. And the second argument is the element I'm looking for. That's, of course, still the same element. So I still pass in element here. Now, for this case down there, I also return a call to find element. But here, that is now my sorted array. Again, a slice of it, but now I'm looking at the other half. Here I know that the element I'm looking for is smaller than the middle element, so I'm looking for the first half of that array now. And therefore, my start index here always is 0, and we go up to that new end index. We can, of course, also keep start index here. That won't have changed, so it still is 0 anyways. Now, of course, again, we pass an element as the second argument here. And that is already all. This is the recursive version of this algorithm. You could rewrite it in various ways, but this in the end does what it needs to do. It gets the array, it has its indexes, we check the middle index, the middle element, and we return if that's the right one. Otherwise, we call the function again, and we call it with a subset of the array we initially got. We pass a brand new array to every nested function call, and that brand new array is either the second half or the first half. Now you see, of course, the way I call find element is always the same. So what we of course could do is we could get rid of it here and move the second call here out of the if-else statement, so that the only thing the if-else statement does is it changes those indexes, and then I call find element with those correct indexes. Now with that, we have an algorithm that almost works, but you will see that we'll still get an incorrect result. We're looking for 99, so we would expect 4 as a result, because it is at index 0, 1, 2, 3, 4. It is at index 4. Yet if I run this, I get a maximum call stack size exceeded error. So we have an infinite loop basically. That's what this error is telling us. And why do we have that infinite loop? We can see it if we console log sorted array and element. And then in the console log output, I scroll to the very beginning of that long log here. At the very beginning, we see that first time we call the function, we get the full array, we're looking for 99. The function gets called again, that makes sense, because 99 is not the middle element initially, it's not 9. That's the next set we're calling the function for. And we see a problem here. The sorted array we're getting here in the second function call should actually be this part, including the 100, but it's not including the 100. And because of that, this does not work. Because for this too short array, we're taking 13 as the middle, so to say, because we round down, and 13 is not the value, and then we again leave out that other number as it seems, since we get an empty array down there in the next line, when we call the function again. So somehow, when we call the function, we're omitting the last element, and that's the problem here. The reason for that is simple. Slice actually omits the last element. So you would have to add +1 here, however, only for this first case here, where you change the start index. If you change the end index, you don't want to add this unless you don't reduce it here. If you don't deduct 1 here, you can use the +1 here as well. Otherwise, the old middle index, which we already can rule out, would again be included in the next array. With this change, if we make that and we reload, now I get 1 as a result. So no error, but still not the desired result. Now why are we getting 1? Well, this makes sense. Let me reintroduce that console log, because that allows us to understand why we're getting this. Sorted array and element. If I now save this and reload, we see this is how the algorithm works now. This is the first time the function is called. Our middle will be 9, which is not 99. So this is the next array we're looking at. We can see this here. Now the middle is 99, and that's why we're done. The problem is this has an index of 1, of course, in that new array. But we're, of course, not interested in the index in the sub-array, but in the overall array. And as a result, we need to carry forward our index to our recursive function calls. Now that's fairly easy to do. In find element, we just need to accept a third argument. We can name it offset. And that's simply the offset which we want to add to the middle index we derive here. And we simply return middle index plus offset here, so that we basically remember the index we had in the array we ruled out. And in the nested function call, when we have a look at a subset of that array, we also add that remembered index. And now down there, when we call find element, we have to forward offset, but we also need to change offset if we're looking in the second half, and only then. If we're looking in the first half, we don't need to change it. But if we're looking in the second half, which is this first if branch here, we need to change offset and simply set it equal to old offset plus our old middle index plus 1. Plus 1 is important here because if we have a look at this concrete example for 99, we have a look at this entire array. Our initial middle is 9, which is of course not the same as 99, so we don't make it in there. Then we go into this if check. Here we check if the element we're looking at, 9, is smaller than the element we're looking for, 99, which of course is the case. 99 is greater than 9. So we make it in there. And then we would change the start index here to middle index, which was the index of 9. So 2 plus 1. So that's 3 then for this call. And then here, offset is equal to our initial offset, which should be 0. We should feed in 0 as the initial offset. So 0 plus middle index, which was 2. So plus 2. So that would make 2. And if we then add 1, we have 3. And why do we need that? Well, keep in mind, it's now 3 with the plus 1. This here was also 3. So now we call find element again with a slice of our original array. That slice starts at index 3, as I just said. So it starts at 13 and goes to end index plus 1 because the end index is excluded. So it goes to the end of the array in the end here. So this is the new array we're calling find element on. The offset we're forwarding is 3, as I just explained. This line gives us 3 for the first function call, and we're still looking for 99. Now we're looking at this array here. Right in the middle we have 99. So this here is true, and hence we return the middle index plus offset, and middle index now is 1, because in the new array, 99 is at position 1, and 1 plus offset is 4, because offset was 3 when we passed it to this nested function call. So we get 4 as an index we return here, and that of course is correct. 99 is at position 0, 1, 2, 3, 4. 4 is correct. If we wouldn't add plus 1 here to the offset, we would have returned 3 instead, which would be incorrect. With all of that, if we save that and reload, we get 4 here for 99. But now let's also validate some other numbers. Let's check for 1, which should give us 0. And it does. Let's check for 5, which should give us 1. It does do that. Let's check 9, which should give us 2. Looking good to me. Let's check 13, which should give us 3. That works. We checked 99 already, so let's check 100, which should give us 5, and that's the case. So that's binary search with recursion. As always with recursion, can be tricky to wrap your head around, but in general, the steps here should be clear. The main difference to the loop-based solution is that in the loop, we just change the indexes, and we then calculate different middle indexes. Here in the recursive solution, we always calculate the same middle index, and we only briefly change the indexes to call our new function again with a subset of the original array. So we really cut the array into slices for the different function calls. And because we're operating on different array slices, we also need to carry forward that offset. Now that's just one possible implementation of that recursive approach here. You could also write binary search with recursion with different approaches, where you just forward indexes to find element and you slice your array up inside of each recursive call. But this approach works fine. Of course, we now have one big question. What's the time complexity of that? Now, when we consider the time complexity of this function here, it's a little bit more complex than what we had before, maybe at least, because whilst we're calling ourselves here, we don't call ourselves n times, for example, because we're shrinking that array which we're passing into the nested functions. So just as with the loop, where we also reduced our array with every iteration, so to say, or we reduced the part of the array we took a look at, we're doing the same here. So chances are that we here also are dealing with logarithmic time, but that's just an idea. Now also one word about slice. Calling slice here, of course, also costs some performance. We're not going to consider this in the time complexity calculation though, because regarding the time complexity, it won't really make a difference. If we would measure performance in milliseconds for very large numbers, for large arrays, we probably would see a worse performance here than here in the loop-based solution where we're not using slice. But that's just a side note. The time complexity, so that the trend, the general nature of this algorithm is not impacted by that. So what is the time complexity here? Well, because we split our problem into smaller problems, because we split that array in half with every nested function call, I can already tell you that we're in the end still dealing with the same time complexities as before. So in the best case, O of 1. In the worst and average cases, we have O log of n. So we have logarithmic time complexity. But if you want to derive this here and not just know it, and you can know it because it's a typical case of splitting the problem into half, but if you want to derive it, there is a theorem, a formula you can apply here for such recursive calls. For, and that's important, for recursive functions, recursive algorithms, where you split your problem, where you split your n into smaller chunks. This formula I'm going to show you will not work for other recursive approaches where you call yourself with just n minus 1, as we, for example, had it in the factorial case. There, this formula I will show you will not work. If you do call yourself and you split your n into half or into thirds or anything like that, this formula will work though. So what is that formula? You can derive the big O, the time complexity of a recursive algorithm with the so-called master theorem. And there you can easily calculate the runtime of recursion, so of the recursive step, with this formula, which looks quite complex. O n at the power of logarithm at base b for a. Now what are all these variables here? A equals the number of subproblems. So how often you call yourself in the end. How often do you split your subset and pass that into a new recursive call, into a new function call. B then is the relative subproblem size. So how do you split your array? Do you halve it? Do you divide it by 3 with every recursive call? That's the question here. And then we'll later also see f of n, so function of n, which will equal the runtime outside of the recursion. We don't have it in this formula though. Now why does this runtime outside of the recursion matter? Well, because the recursion in the end is not just that one line where you call yourself, but also the entire code besides that. And you have to differentiate between 3 cases when you're dealing with the master theorem and you want to derive the overall time complexity of an algorithm. The first case is that the recursive step does most of the work, that it has the biggest runtime. In that case, the overall algorithm runtime is that same function you're seeing up there. If you have the same amount of work inside and outside of the recursion, then this would be your formula for the overall runtime. And if the non-recursive part does more work, which will rarely be the case, this would be your formula. So you would then ignore the runtime of the recursion and just focus on the other runtime. Now that's very theoretic. Let's see this in action. Let's have a look at our algorithm here. And let's start with the runtime of the recursion part. So with this first formula, what's the big O for just this recursive step? So I'm really just talking about this line. And yes, you are calling the whole function there again, but that's the idea behind the formula. With the formula, you can split this up. So what's the runtime of just this line? Well, let's start with A. the number of sub-problems. How often do we call ourselves? We call ourselves once. So A would simply be 1 here. Let's note this. A is 1. Now, B was the subproblem size. So do we split it in halves, in thirds? What are we doing? In the end here, we're splitting our array in half. That's in the end what we're doing, right? We're always splitting it in half. So B is basically the number by which you divide, so it should be 2 here. This allows us to solve this formula here. We have n at the power log at the base of b, so of 2, of a, which was 1. So here we have big O of n at the power of log b for a, so that is big O of n at the power of log base is 2 of 1, and that you can simply Google that. Here, if I just add these numbers real quick, I see 0 is the result of that. So that is essentially big O of n at the power of 0. And that, something at the power of 0, is simply 1. So, long story short, this recursive step alone, this line alone, has a constant runtime. Now, that's not the overall algorithm runtime. That's just of the recursive step with this formula. Now, to get that overall algorithm runtime, we need to have a look at these different cases to get the overall algorithm formula. And here the question is, does this recursive step, which has a time complexity of O of 1, do more work, less work, or an equal amount of work than the rest of this function? So back here, this line here, we learned that is O of 1. So after this comment, this line. What about the rest here? Well, we have no loop in there. We have no nested function calls. We call math floor, but that does not impact this. This is basically constant time. So we don't have anything special there. We got if cases, but those don't add anything to the time complexity. They might just lead to some best or worst cases. But long story short, without any loops, without any nested function calls, this rest here, the part here, is also O of 1. It's constant time. If our function was just that, it would always take the same time. It's constant time complexity. The time this takes does not really depend on n. It does not depend on the length of the array. Hence, the time complexity of the recursive step, O of 1, is the same as the work outside of the recursive step. So on this slide, we have this case here. Same work inside and outside of the recursion. So the overall algorithm formula for deriving the overall algorithm time complexity is this formula here. Hence, we can say that the overall algorithm time complexity here is O of n at the power of log b for a times log of n. Now, we already learned that this part here is just 1, right? That's the same as up there. So in the end here, we have O of 1 times log of n, and that, of course, is O log of n. And that's how we can mathematically derive this runtime here. Now, important. This is a formula which you can learn. It's not too hard to memorize. Sometimes this might be useful, especially if you're in an interview situation and you want to show that you know it, or you're coming up with an algorithm there where you don't know the runtime by heart and you're not sure if you're thinking about it correctly. Then you can take this formula to derive it. If you have such a recursive case and you're splitting your subset in the factorial function where you just deduct 1 or something like that, this does not work. You really have to divide your problem into smaller subproblems to use this formula. But then you can use it to mathematically or pseudo-mathematically derive this time complexity. Now, if you're able to just see the time complexity, as we actually can do it here, we can see that this has to be logarithmic time because we're splitting it in half with every iteration in the end. then of course you don't need to go through that formula. Since this is a course, I find it important to teach the formula. It can help you, especially when working with algorithms you're not sure about. But if you just look at a certain algorithm, at a certain function, and you see that there is one recursive call and you just split the problem in half and there is nothing else in there, there is no loop or anything like that, well, then you of course should know, at least by the end of the course, that this probably is logarithmic time, and you then don't have to go through that entire function here.